Nick Deardorff, Chairperson of the Geoscience Department, and I'd like to welcome all students, faculty, family and friends, and alumni to the 47th Annual Geoscience Day. This has been a strange and challenging and often stressful year. 1 year ago, we were hosting our first ever virtual Geoscience Day due to a global pandemic. Here we are again, virtually gathered because the pandemic persists. Additionally, in the past several months, there have been large changes announced at IUP, including a reduction in faculty and staff and a general restructuring across campus due to financial necessities. This includes the merging of 2 colleges and several departmental mergers. As many of you are aware, our Geoscience Department is in the process of merging with the Department of Geography and Regional Planning. Our newly merged department will be called the Department of Geography, Geology, Environment, and Planning. These changes across campus, as well as the pandemic, cast a shadow over this academic year, creating additional anxiety and uncertainty. However, through it all, our faculty and students have stayed strong. They've pushed forward. Our faculty have evolved and recreated and manipulated their courses into a virtual format. Our students have had to adjust and learn how to succeed scholastically in pajama pants. And our graduating seniors have continued to advance their senior research projects, which we will hear about today, and have learned to present their research at virtual conferences in virtual formats, as we will see today. In short, it has been a challenging year, but we've made it. The end is nigh. All right, that sounds a little ominous, but I mean the end of the academic year is coming. It's nearly over. We have persisted and pushed through this dreadful year, and we are almost out the other side. And we have prevailed because of the strength of our geoscience community, because of all of you. In this challenging time, we have leaned on each other and supported one another. Our community has exhibited great empathy and understanding and flexibility, perhaps flexibility most of all. For this and many reasons, I'm very proud to be a part of this department, and I feel we will come out stronger on the other side. I should note that our department is changing. As we merge with the Department of Geography and Regional Planning, some things will be adjusted. Some departmental traditions may be altered or even abandoned. However, new opportunities will also arise in this larger and stronger department, and I welcome our new colleagues into our community. What will not change is the quality of the geoscience education we provide and the quality of the student that we produce. We will also not abandon Geoscience Day, although the name may change and geography and regional planning students may be included in the future. This is a special day in which our students, especially the graduating seniors, will remember for the rest of their lives. Our tradition of torturing our students by making them publicly present their research will persist. In fact, this year we're also including a batch of juniors in our Geoscience Day who are just getting their research projects started. I'd like to take this time to thank all of our student presenters for the hard work they have put into the projects that we will hear about today. A special thanks also goes out to the faculty who have mentored the students through these projects, and particularly to Dr. Cercone and Dr. Farnsworth, who have helped to prepare the students for this special brand of torture that we call Geoscience Day. Finally, thank you to all family members tuning in for your support of our students. And thank you all for joining us today. So now I'll turn it over to Dr. Farnsworth, who's going to get things started.
Good morning. Thank you, Nick, very much. That was a great introduction. And so we're going to go ahead and move right into our Geoscience 470, which is our junior seminar on research methods. And our first speaker this morning is Susie Adams. So Susie, you can turn on your screen. I forgot to let everybody share. You should be able to share your screen now. Is it letting you do that, Susie? There we go. And Susie's going to be talking today about her research project that is with Dr. Lewis and set in Taiwan. So Susie, it's all yours.
Hi everybody, my name is Susie, and this morning I'm going to be presenting on late-stage plastic and overprinting brittle structures in exposed river outcrops in Taiwan's eastern central range, but I'm going to be focusing more on constraining the overprinting brittle structures. So just a quick background and tectonic setting of Taiwan. So Taiwan is an island off the coast of eastern China, and approximately 5 million years ago, the Luzon volcanic arc, which is located here, and the leading edge of this Philippine sea plate collided with Eurasia's passive margin, which is located here in the lighter blue, and it created the mountain belt that we are currently studying now. So this collision appears to drive some of the highest uplift rates in the world on the order of 5 to 8 millimeters per year. And now this may not seem like a lot of uplift, but geologically speaking, over a period of about 1 million years, this results in about 5 to 8 kilometers worth of uplift. So we're focusing on the East Central Range, which is located here. And here's just a neat geologic map of the belts in the Eastern Central Range. So these belts are comprised of schist and slate and divided into the 𝐂𝐴𝐬𝐞 and 𝐬𝐚𝐫 belts. So here we will synthesize observations over a long strike distance of approximately 100 kilometers. Now my data will be predominantly further south. So we are hoping to provide constraints on the geometry and kinematics of brittle structures formed during Taiwan's exhumation of the metamorphic core by documenting the plastic to brittle transition. So a little bit about what the plastic to brittle transition is. So when Taiwan's metamorphic core was closer to the mantle, it actually allowed the rocks to flow plastically as it exhumed. And as the rocks began to exhume, they crystallized, capturing the plastic deformation. Now, as the rocks continue to exhume, they began to cool down and break brittly into what are known as our joints and faults. So what joints are there fractures in the rock, as you can see in this picture here. And what they are is just little cracks, and fractures in the rocks that don't cause any displacement. They just these ones we are actually showing that they accommodate the northeast southwest stretching direction. And actually to the left of the joints are what we refer to as veins. And what the veins are just joints that have precipitated with minerals. And we also believe that veins are the bridge between the plastic to brittle transition. And so the furthest to the left is what we refer to as plastic deformation, and also as referred to as S3, that actually my fellow peer, Lauren, will be presenting on later today. So here, just an overview of the rivers that we've studied. So here are all the rivers and outcrops that we have visited and collected data from. And my 3 that I'll be specifically working on for my research will be in southern Taiwan. And as you can see, the Southern Cross Island Highway, the Dawloon and Jinwulu rivers, even though the highway, it was just cross-cut, so we can see we've collected data and exposed outcrops that provided data. So we group those together because they're geographic location. So I'm going to argue the hypothesis that exhumation in the Eastern Central Range is in part accommodated by organized northwest striking joints that evolve into normal faults. As you see in the pictures here, there are joint sets that are steadily evolving into brittle faults, as you can see, because they're wanting to move away from each other. So what is a fault? As I mentioned before, because these joints will eventually evolve into a fault. A fault is a fracture in a rock that shows displacement in response to movement. In this case, the movement would be the exhumation of the metamorphic core as it moves to the surface of the earth. So to test this hypothesis, I'm going to be looking at robust fault data sets, such as this one along the Dawloon River. And as you can see, these are some pictures of some faults. There should go. So this is actually a fault zone we have a UConn grad student for scale. This is the hanging wall of a fault. And over here we have the lineations as lighter part, which shows the slicken lines, which would just show which direction the fault is slipping. So I'm going to take rivers and rivers with data like this that have field observations, photos, and faulted lineations, and just build a detailed case of the analysis of the data. So I'll just provide the fault zone, what it looks like, the textures, the breccia present, lineations, and any local joint data, and describe and use it to describe what this type of brittle deformation looks like and how it represents the passage of these rocks as they move from the plastic to brittle regime. So ultimately, I'm going to be showing what the end stage of deformation looks like. and how documenting the geometry and kinematics, how it's documenting the geometry and kinematics of these fault zones. So to do this, I'm going to be using software such as QGIS, which is a mapping tool where I'll be constructing maps of Taiwan and plotting the geographic locations and compare them to each fault zone. So I'll also be using StereoNet and FaultKin to plot the attitudes and sense of the faults to create fault plane solutions and just have a better understanding of what the faults are doing and overall. Why does this matter? So Taiwan is located on a unique plate boundary where an oceanic plate, a passive margin, and a volcanic arc meet. So by providing constraints on plastic and brittle deformation, we will be able to provide data for future scientists to use in their research and explore new observations in Taiwan to give a better understanding of the tectonics in this area. Now, Taiwan is very dynamic and will always need new research conducted. I would very first like to thank Dr. John Lewis for introducing me to tectonics and assisting me in learning new ways of spatial thinking, as well as always being very patient with me throughout this process. I would also like to thank Dr. Katie Farnsworth for teaching the 470 class this semester, as well as Lindsay Almond and Lauren Donati, who are past and current members of Team Tecto, which is just the nickname for a research group, for always being there when I need advice on a poster or a presentation and being there to practice my presentations beforehand. Lastly, I would like to thank the NSF for providing funds for research, for this research to be possible. Thank you. I am now open to anyone who has any questions.
So feel free to unmute your microphone if you're within Zoom, if you have a question, or you can put it in the chat, or if you're on YouTube, you can type a question in the YouTube chat and we will convey it to the speakers. It looks like you're going to escape today, Susie, without any questions. Thank you so much for your presentation.
Thank you.
Nick, did you have a question?
Sorry, I was having problems unmuting for some reason. Well, I was just going to ask if she could, so I know Susie's already been to Taiwan once or twice, just once? Once. You've already kind of collected samples. Can you give us an idea of, you said you were going to collect data at these locations along these, road cuts and along the rivers. Can you give us an idea of like what the sample collection is like? And are you going to be heading back there again to do a little more?
It's still up in the air. I mean, COVID depending if we can go back in the winter. But as for like samples, we can't really, I mean, the only time you can really collect samples is for like more of the plastic deformation. But for the faults and the joints, we'll just be collecting it with like a Brunton compass and just finding the strike dip and the rake and the sense of the fault and plotting it all in FaultKin and StereoNet.
Okay, thank you.
We do also have a question from YouTube. It's coming from Lindsay, and she wants to know if you're going to look into the faults that they see in the high country at all.
That would be, I hope we can. I have to talk with Dr. Lewis, of course, but we'd have to visit to go collect data for in the high country. So if we were able to go back in January, I would hope we could hike to the high mountains and collect fault data up there.
Great. Thank you so much, Susie. And you are good to go. And so Christian, you're up next. So if you can turn on your video and microphone and share your screen for your presentation.
No problem. Okay, so everybody's seeing that?
Yeah, it looks great. All right, so our next speaker is Christian 𝐕𝐬𝐳. He is going to be talking about his research proposal on using diatoms to understand climate. It's all yours, Christian.
right, so a lot of you already know me, but I am Christian Vizza. I'm a junior here in the Geoscience department, and I'm working with Dr. Warnock to catalog diatoms from the Southern Ocean and interpret them to get a better picture of climate of that region in the age range of the Mid-Pleistocene Transition, which is about 900,000 years ago. But briefly, before I dive into the research I'm focusing on, it's important to mention the LR4 stack. It was compiled in 2004 and published in 2005 by Lorraine Lysecki and Maureen Ramo. It shows the oxygen-18 record from present day back to about 5 million years ago. And this is a portion of that record that dates back from present day to 1.8 million years ago. Oxygen-18 is its own proxy record for ice volume. So a record like this, averaged from 57 different sites all across the planet, can give us a picture of when ice ages occurred. More oxygen-18 means less ice, so the peaks are interglacial periods and the troughs are glacial periods. They're also given numbers called marine isotope stages, with evens being cold and odds being warm. The LR4 is important to really any climate reconstruction from the past 5 million years as a tool to compare other data against, including the research I'm going to be doing, and literally every single piece of literature I had to read in preparation for it. So you're going to be seeing this again throughout this presentation. But the crux of this research hinges around the concept that diatoms can be a compelling proxy record for all sorts of climate data we can no longer directly measure. Their total abundance alone can be an indicator of glacial cycles, as shown on this tuned graph by Matthew Confist and his team. Higher diatom abundances are linked to periods of increased oxygen-18, as described by the LR4 stack. Sorry, my dog is barking. Which you can see here on the left side of the diagram. It's the same one as before, just turned on its side. There are also more fine details you can tease out by looking at individual species abundances. For example, Actinocyclus actinochilus can act as a sea ice indicator, telling us if there was sea ice in the vicinity of the sample site, and looked at through time, it can tell us whether that ice has increased or decreased. 𝐂𝐴nthia antarctica is more present during productive cold periods, letting us know that the water was cold but also high in nutrients. So using these methods, we can compile a compelling history of the site where the sample was pooled, if only we have the time and the patience to catalog all these microscopic little guys. As for that location, I'm working with core samples collected from the International Ocean Discovery Program on Expedition 382, which took place northwest of the Antarctic Peninsula. Site 1538 hole A is here, just to the west of the Antarctic Peninsula. More specifically, I'll be cataloging cores 20 through 24, which amounts to 75 samples when tuned to their proper ages by comparing them to other stratigraphic and magnetostratigraphic records should align with the time of the Mid-Pleistocene Transition, which again, about 900,000 years ago. The method for cataloging these diatoms is to extract and weigh out about 0.025 grams of sediment from the core interval, then using a mortar and pestle lightly break that sediment up without using so much force as to destroy any of the silica diatoms. We're not looking to grind anything up so much as just deconstitute the mud. The powdered sample is then placed in a small jar mixed with a solution of hydrochloric acid and hydrogen peroxide and left to stand for a few hours to dissolve out any mud or carbonates, leaving just the silica behind. The solution is then mixed and dumped into a 2-liter column of water with a pair of slide covers inside. The remaining sediments allowed to settle through that column and onto the slides, and then slowly drained and allowed to air dry until the slides are dry and ready to be viewed through oil immersion microscopy. Finally, I look at each slide systematically, moving from field of view to field of view until I've identified at least 300 individuals of varying species and logged them into a spreadsheet for analysis. As for the Mid-Pleistocene Transition, it's a time of upheaval in our glacial cycles between marine isotope stages 22 and 16. So this is again the LR4 stack that shows when our ice ages were. The Earth's ice age clock changed from being on a 41,000 year schedule to its current 100,000 year schedule. And while the glacial periods have gotten further apart, they've also gotten more intense. So you can look at the two sides of this record and see that under the 41,000 year world, the peaks are closer, but not as high as they are under the 100,000 year world. And then the area of the box in between is the Mid-Pleistocene Transition, which is where I'm going to be focusing. So there's no current clear consensus as to why that shift occurred, or even what's currently driving the 100,000 year periodicity. It could be linked to eccentricity. It could be a combination of precession and obliquity. It could be something else entirely. As for causes, there are teams looking at everything from carbon dioxide being sequestered in the deep ocean to the removal of regoliths in the northern hemisphere to just dust being generated by the glaciers. Several scientists, including Dr. Ramo, who is the R in the LR4, believe that this shift could have been caused by the East Antarctica ice sheet expanding from a terrestrial margin to a marine one about 1 million years ago. Southern waters would have flowed northward as the front moved, as they've diagrammed here by Heather Ford and Thomas Chalk. You can see in that middle diagram during the 900,000 year event that southern content waters would have flowed northward, flooding that basin. My hope is that the catalog I'm building from these cores might be able to provide some insight into that process. There are several diatoms I would expect to find in this record that act as sea ice indicators, including the one I had mentioned earlier, Actinocyclus. Fragilariopsis curta and Thalassiotermita are also sea ice indicators that what I would expect to find during this record. And so if the East Antarctica ice sheet did expand during this time, I would expect to find increases in these kinds of diatoms over the course of this. So I've currently started the process of preparing slides to catalog. I'm working on learning the individual species and their visual identifying features. This gets a little tricky because of the age of the samples. It means a lot of the diatoms I'm going to be looking at look like this. They're just kind of broken and beat up. They've seen better days. But that's certainly not to say that I haven't seen some very nice samples just on the 2 slides that I've already prepared. There are some really nice round centric ones, and there are some long football shaped ones where both the points are very visible. It's just certainly not going to be the norm. I've also built a spreadsheet of my own to log my progress through the samples, and as you can see, the work has truly just begun. But I'm excited to get further into the research and dig into the data. I really enjoy PowerPoints. It's a strange quirk, but I like data in the little boxes. And so I think this is going to be an engaging project for me, even at its most tedious. The work is ongoing, but that's true of pretty much every study and branch of science. I'm just happy to be able to roll up my sleeves and contribute, maybe add a little to the body of knowledge instead of just sitting and listening. So that is pretty much my presentation. I'm also happy to take questions. You may just have to listen to my dog since he gets confused when he can hear voices and can't find the people to go along with them.
Great job, Christian. Thank you so much. So we do have a question from YouTube. The question is, what made you want to explore this type of work?
I kind of fell backwards into it a little bit. As I've gotten more into sedimentology and stratigraphy, it's gotten more and more interesting to me. I've also become kind of deeply passionate about the climate, and so any kind of work I can do to help with climate reconstruction is fine by me. And the Mid-Pleistocene transition is just really interesting to me because it's kind of right on the edge of like, okay, what do we know and why do we know it? And no one's really 100% sure what was going on at that time. So yeah, like I said, really any chance I can have to add to the body of knowledge would be great.
Thanks.
I've got a quick question.
Yep.
Christian, well, first I need to apologize. I've been mispronouncing your last name for years now, so I'm going to remember this, Visa, like Riza, so I apologize.
You're good.
You mentioned that diatoms can be used as sea ice indicators. How does a diatom tell you that there was sea ice at the time? Can you kind of describe that just a little bit?
Yeah, so many of them grow in just very specific environmental conditions. So some of them require a regular influx of fresh water from melting ice, and so they'll only form on like the polar margins where the glacier is meeting the ocean. Some of them only form in like specifically warmer or colder temperatures. And so you can say like if we can find that the ocean temperature in general was a certain temperature, but there are colder diatoms forming in this location. There was probably ice nearby.
Okay, thank
Great.
you.
Thanks. All right, we'll need to move on to our next presentation. Thank you very much, Christian. All right, so our next speaker is Caleb. You can go ahead and share your screen. Great. So Caleb is going to be talking about a phase 1 environmental assessment that he'll be doing on a property, I think in his hometown. All right, you're all up, Caleb. It's all yours.
All right, so I'll be doing my senior research project as a phase 1 environmental site assessment. And for those of you who don't know, phase 1 assessments are reports that are prepared for real estate holdings that assess possible contamination or present contamination near property before sale or addition. And the site I chose was a site from my own hometown. It is the Mountain Union Railroad Museum. It is located right here, this little building right here. And it is near a inactive railroad and a active railroad. And the research question that I will be answering is there any potential contamination that the museum would need to know about before they either put their building up for sale or expand it? And how I will be attempting to answer this question is by the use of Sanborn fire insurance maps and previous research from what the Sanborn fire insurance maps show me, which they, for those of you who don't know, they were used from 1866 to 1977, and they kind of allowed fire insurance companies to assess their liability on buildings in urbanized areas. This is one that I have found from looking at them. And what it shows me is an old tannery that used to be right in this area right here. And right here is the museum in relation to it. And it was an old tannery. Then it is now a construction field that is used for the storage of this particular construction company's equipment and supplies. The next area is one of 3 of Mount Union's brickyards. Mount Union used to be a big brickyard town, made bricks all the time. We learn about it in high school. And it is this area right here. And right here is the museum. And this brickyard was owned by Harps and Walker Refractories. And it was later turned into a landfill for this company. And it was where they dumped a lot of the waste from the other 2 brickyards in the town. They dumped it in here, and then you can't see it I don't have a picture of it, but like right around this area, there are 2 pools where they dumped a lot of their waste. They also stored surplus material in these buildings right here. And then there used to be little silos here. And later, after a while, it was then put up for sale. And a local member of the community bought it. His name is Chris Davis. And when he bought it, he had tests done on the area and in the 2 pools to see what kind of contamination is there. And I got a hold of him and I talked to him about it, and he actually has offered to give me that report for my research. The next area is the museum building itself. The museum building itself used to be a furniture factory, and then later was a railway depot, because right here's this used to be a main railway. Now that's just not used anymore. And then it was turned into a museum, and kind of the stuff that they do at the museum, they have exhibits. And then on Halloween and Valentine's Day, they run a haunted house. I have so far looked up previous research on these areas. And what it has shown me is there was a study in Poland that looked at a couple of Polish old tanneries. And some of the things that study found, one of their main findings were high amounts of chromium. And the particular one that they found was hexavalent chromium, which causes liver and kidney damage. And the reason that they have found high levels of chromium near these tanneries is because chromium is actually used in the tanning process of leather. What they do is they take the leather and they put it in an acid bath and a salt bath, and then after that they take it and move it to a chromium bath, and then from there just the leather continues down the tanning process. And then what they do is usually they would dump it into pools, or they would just dump it in the ground. They didn't, back then they didn't really dispose of it properly. And what another thing I will be doing is kind of going to the library and researching if they're how this particular tannery disposed of their waste, whether they just dumped it or they disposed of it properly, which at the age of the tannery I don't think they did, but I will probably find that out. And then for the brickyard, I have 2 papers that were done in Kentucky. They complement each other. They were done a couple years apart. And what they did was they looked at the legacy contamination of old brickyards. And their findings were, one of them was high levels of chloroethene, which is used as a gasoline additive. It's also used in plastics and dyes. Some of the effects of this is long-term exposure causes hangover effects, like vomit and nausea, after a long night of drinking. And then another contaminant that they found was high levels of trichloroethene, which is used in industrial solvents, and that has been known to cause cancer. And then for the furniture factory itself, I haven't found any papers yet that goes over the legacy contamination of old furniture factories, but I will be continuing to dig on that. And then some other papers that I will be looking for is contamination of inactive railways and active railways, because one thing that first comes to mind when I think of railways are the railroad ties, and those are soaked in creosote, and that can leak into the ground. Other papers that I will be looking for is like legacy contamination of landfills, both current landfills and inactive landfills. And then I will also be looking for papers that detail legacy contamination of active construction fields, mainly ones that are used for storage of their equipment and all of their materials. And these are the citations for the papers that I referenced. And is there any questions?
I don't see any from YouTube yet, but they're always right behind us. Does anyone have any questions for Caleb? All right, great. Thank you so much, Caleb.
Thank you.
Next up, we have Eric. So Eric, if you can turn on your video and microphone and share your screen. Awesome. There it is. All right, so Eric's also doing a phase 1 environmental assessment of a very interesting site. And so we will turn it over to you, Eric. Thanks.
All right, can everyone hear me okay?
Yep.
Sorry, yes.
Okay, thank you, John. And thank you, Dr. Farnsworth. Hello, everyone. My name is Eric Reynolds, and I'm a geoscience major here at IUP. My proposal's goal is to highlight the necessity for a phase 1 environmental assessment of Babcock and Wilcox former nuclear production and waste burial site located in Parks Township, Pennsylvania. A little bit of background on Babcock and Wilcox. They're a worldwide power industry giant that is still active today. They were founded in 1867 in Rhode Island and later moved to Ohio. Their goal was to create safer steam boilers, in which they did succeed on and build a pretty lucrative business doing so. After decades of success in the boiler business, having completed numerous federal contracts, they shifted some of their focus towards nuclear technology. This was during World War II, where they provided components for the Manhattan Project and manufactured parts for the world's first nuclear submarine, which was the USS Nautilus, which you can see in the top right photo here. Later on in the 1970s, they were also the company that designed and built the nuclear reactor that was involved in the 3 Mile Island incident. Since then, they've really ramped up their renewable energy technology, and they've been heavily focused on that since then. And this brings us to the Parks Township site. It's a 44-acre site located in rural Parks Township, and that sits in between Leechburg and Vandergrift, Pennsylvania, which is roughly a 45-minute to an hour drive from IUP. During the period of 1961 to 1970, the site was owned and operated by NUMEC, the Nuclear Materials and Equipment Corporation. And it was used for the burial and disposal of both nuclear and non-nuclear waste that was fabricated at a plant in nearby Apollo, Pennsylvania. The nuclear waste that was buried there was used in the process that converts enriched uranium into naval fuel, which powered the nuclear submarines that were discussed earlier. A company called the Atlantic Richfield Company bought all of NUMEC's stock in 1967 and subsequently sold it to Babcock and Wilcox in 1971. And they continued to produce and bury nuclear materials on site until 1980. Pictures here are all of that site during different time periods. Photo in the top right here is during early years of production and waste burial. The one down here is somewhat more recent, but it has to be before 2011 because the Army Corps of Engineers was tasked with remediating the property, and they built this building seen in the bottom right photo on this portion of the property, which is where I suspect most of the nuclear material is buried. So my intention is to carry out a phase 1 environmental assessment of this site to evaluate the current day impact of radioactive contamination that is still present at the location today. Due to the length of time that the site was actively producing and burying nuclear waste throughout the transfer of power between 2 nuclear power giants, it is not only suspected, but in fact likely that contamination still poses many negative threats to the surrounding environments and inhabitants. Since the burial site is located on top of a hill and the 𝐂𝐝𝐵 River is directly downslope from it, the 𝐂𝐝𝐵 has been subjected to contamination by this site and similar sites such as the aforementioned Apollo site, which is located upstream from this facility for decades. Also located near the site are a number of residential communities, and it also includes a business park. Just a few miles further downstream is the town of Leechburg. And since the site is located so close to the river, and since there are numerous populations nearby, it is absolutely vital that the groundwater near the property is properly tested for nuclear radiation, which can be done with a gross alpha test. As you can see with the map here, this is the site. This is that building I highlighted earlier. The residential community here, there's one across here. And this used to be actually an old airport. And then the business park is up here. I couldn't get it in the shot. And then this is the 𝐂𝐝𝐵 River here. And further down the river, downstream is Leechburg, Pennsylvania. As far as what was produced and buried on the site is concerned, it was mostly the preparation of uranium fuel, the fabrication of plutonium fuel, the production of zirconium and hafnium bars, and smaller amounts of thorium and americium were worked with as well, all of which come with their own health and ecological risks. Exposure to uranium, for example, is a known cause for renal failure, diminished bone growth, and can even go as far as damaging your DNA. which also brings with it its own plethora of health issues that can stem from that. And plutonium is also known to be the cause of various blood cancers such as lymphoma and leukemia. The site is known as what's called a shallow land disposal area. This early on in my research, it's unclear what techniques Babcock and Wilcox, along with 𝐂𝐚𝐬𝐢𝐞, used to contain the materials. However, my hypothesis is that there is in fact sufficient evidence that further investigation of the site will need to be done after the completion of my phase 1 environmental assessment. If the project is greenlighted, it is my intention to get in contact with the Army Corps of Engineers, who again are in charge of the remediation project, to find out exactly where the waste was buried and how. According to a spokesperson interviewed by the Wall Street Journal, it is thought that the burial protocols had been violated. And typically speaking at these sites, waste is put into containers and placed in constructed vault where they are full. When they are full, they are covered and capped with an impermeable membrane to prevent leakage, and then buried with topsoil within rows of trenches. As you can see here, it's typically buried at a depth of roughly 15 to 200 meters. And these are just the containers right here inside of those trenches. Whether or not the waste had been disposed of properly at the Parks Township site, again, remains unclear. And that's all I have. Thank you for your time and thank you for listening. I'd also like to give a huge thanks out to Dr. Karen Rose Cercone, who has helped me throughout this project. Does anybody have any questions?
Great, thanks, Eric. Anyone have any questions for Eric?
I've got one, Eric. Do you know,
Sure.
in your research, have you come across anything explaining why the Army Corps might have chose to build over the buried nuclear material as opposed to potentially digging it up and doing something different with it?
I know that when they went in to start the remediation project, the situation was a lot worse than what they had previously thought. So they put a delay on it. I think until 2031 is when they're supposed to start the remediation project back up again.
Great, we'll just give the YouTube folks just another second since we missed a question last time.
Eric, do you think you said you got to reach out to the Army Corps of
Right.
Engineers to ask some pointed questions about their techniques? Do you think that they will provide the information that you need?
That's unclear. Since it is the Army Corps of Engineers, I'm not sure what information they'll be able to give me, but I'm hoping that they did do a gross alpha test on the groundwater, at least, and hopefully they'll be able to at least share that with me. Also, topographic maps would be nice.
Great, thank you very much, Eric, for your great presentation, and thanks to all 4 of the students that just presented in session 1. We're gonna take a break. We'll be back at 11:10. So we went a little bit over, so in about 9 minutes. So take this opportunity to stand up, stretch, and make a quick run to the restroom if you need to. And we'll be back in about 9 minutes at 11:10.
Hello again, everyone. We're going to get started here in just a moment. I just wanted to take a moment and say thank you to all of our alumni for joining us here today that are streaming on YouTube and providing questions. We're going to continue with the same format as earlier. If you missed it earlier, our students will be presenting for 8 minutes or so, and then if you have any questions, you can type them into the YouTube chat, or if you're in the Zoom meeting with us, you can just unmute yourself and toss it out there. So we'll get back with you in just a moment. We're having some mild technical difficulties. I'm not sure we've ever had a section where we didn't have mild technical difficulties running this.
That is very, very true.
It's our second time running it, and we've had 2 or 3 already today. And last year when we did it, we had at least that many.
All right, so I think we're sort of out of luck because of these technical difficulties with our first speaker. So we will go ahead and continue our break until 11:20. So we will give you all an extended break here. We want to keep on schedule because people had particular times they were expecting to talk. And so we'll be back in about 6 minutes. All right, as we get ready to get started again, thank you and welcome back. So our next speaker is Molly. So Molly, if you want to go ahead and, hey, look at that, there you are. You can go ahead and share your screen for us. Great, well, thanks everyone. Welcome back to session 2 of our 470 presentations. And so our first speaker had technical difficulties and wasn't able to join us. So we are now sort of on our second speaker, just getting started. And so Molly's going to be talking to us about a water budget study located here on a stream here, right here in Indiana. So it's all yours, Molly.
Okay, so hi everyone. If you don't know me, my name is Molly Rabin, and today I will be telling you all about my proposed research I'll be doing with Katie on the water budget of Marsh Run Watershed and my steps and processes on how I will be doing so. So to start off, you might be asking yourself, what exactly is a water budget? Simply, a water budget is a measurement of all water that flows in and out of a watershed, where the water is being added or input and removed or output. However, since we know that water moves in a cyclical motion, when water is being output, it's really just being input into another water system. By determining a system's water budget, we're able to evaluate the different sources that bring in new clean water or other materials, and then the corresponding discharges as well. Water budgets are beneficial in helping us better understand how different watersheds perform and how to keep them from drastically changing and possibly leading to things like flooding. Changes in things like land use, population, climate, hydrology, and more can lead to small to drastic positive or negative changes in a watershed. In this simple diagram here, you can see precipitation being added to the watershed, equaling the evaporation and evapotranspiration from soil and surface water and plants, plus the change in the amount of water storage and the total water flowing out of the watershed. So looking more closely at my study area, Marsh Run is one of the 4 watersheds to make up the Indiana region, where the other 3 are White's Run in this purple color, Stoney's is in this red, pink, and McCarthy Run is on the left here in green, leaving Marsh Run in the yellow here on the right. Marsh Run is also considered a headwater stream, meaning that it is the smallest part of the water flow network and the furthest point from the network's endpoint. So multiple steps and different methods that can be applied over different scales will be necessary to monitor and obtain the data needed to determine the water budget of Marsh Run. So first, looking at conductivity and the amount of materials passing through and dissolving in the stream, where the more total dissolved solids in the water, the more conductive the water will be. For example, if your sample results come back with a higher conductivity, this could mean it just rained that day or more materials got flushed into the stream through runoff like road salt in the winter months, and more clean water coming in again from precipitation, rain, or snow, where conductivity is just the measure of the water's ability to pass an electric current. Temperature also affects conductivity, where the warmer the water is, the higher the conductivity. And then for most things I'll be monitoring, we can use data loggers and rain gauges. Specifically looking at the Solness data loggers, these are very effective when it comes to helping determine the inputs and outputs of a water system. The loggers collect data on air pressures as well as water pressures, temperatures, and you can collect conductivity from them as well. It's greatly beneficial to have multiple loggers and rain gauges throughout the stream, just so we can get more data from different locations. These loggers are able to hold thousands of data sets and require little maintenance once set up. Through downloading an app, I'll be able to transfer the data collected to my device or computer and then analyze it. The loggers are set up in a stream that's attached to a wire, fixed to a tree or post of some kind. The logger itself is placed in a PVC pipe that has small holes through it to let water flow through it easier. And then the PVC pipe itself is attached to a steel rod that is set in the stream bed to hold it in place. And then for the rain gauges, water comes through a funnel or just enters through the top of the bucket. As it gets filled up, the bucket will begin to tip. Once it tips, it gets recorded, and then by showing how many times the bucket is tipped, you can then determine the amount of precipitation that occurred in that area. By going out to the different parts of the streams where the loggers and rain gauges are located, the necessary data will be recorded along with water samples to be examined. So on the left here is the data logger, and on the right is an example of a rain gauge. So why does all this matter? Why do we need to better understand how watersheds perform and what their water budget is? Really, just knowing a water system's water budget is immensely helpful in learning more about different changes in things like hydrology, population, land use, and climate, and how they affect the watershed. So in conclusion, natural processes and human impacts on stream flow and water quality can negatively affect human life around and near the area and the aquatic life that's in the stream, due to these activities allowing more pollutants and runoff and different water into the watershed and stream. It's important to know how much water is flowing in and out of the stream and watershed to be able to keep it balanced from, again, letting things like flooding occur. Through this research study, I'll be able to further understand the water budget of Marsh Run watershed. And if you guys have any questions.
Great. Thank you, Molly. Anyone have any questions for Molly? We'll give the lag on YouTube a chance.
Thank you.
Looks like you're just getting compliments and not questions today. All right. Thank you so much, Molly. And we'll go ahead and get our, oh, here's a question that came through for you, Molly. Just kidding. Over what time period will you be collecting data?
So I actually haven't been able to get out in the field yet just because of the pandemic and not good timing with everything right now. I'll be doing the 𝐂𝐴 program this summer when I'll collect a lot of samples through the summer months, so June, July, and August before the school year.
Great, thanks. All right, thanks, Molly. All right, so the last in this session this morning is Gavin. So if you want to get your screen up and going. Great. All right. Hey, Gavin, we're just going to wait just a couple of minutes. We try to stay on the time scale. So we'll just give everyone your adoring fans who are joining us on YouTube, let them arrive to be able to see your presentation. So just to let everybody know, after Gavin's talk, we'll have a break until from about 11:40 to 11:55. And so that'll be another break to get up and to grab a sandwich or something before we have the seniors who are in Geoscience 480 give their presentations over the noon hour. And then following them after another short break at 1:10, we have our keynote speakers for today. We have Jerry Hatcher, who's an IUP alum, and Dr. Jonathan Warwick, both from the Pacific Coastal and Marine Center of the U.S. Geological Survey in Santa Cruz. So that's what's coming up later today. So, all right, Gavin, we'll hear from you. And Gavin's doing a project looking at microplastics in our waters in the area. So it's all yours, Gavin.
Okay, well, thank you. Yeah, so I'll just get to the next slide here. So microplastics are simply just small pieces of plastic debris in the environment caused by the breakdown of consumer products and industrial waste. Microplastics are dangerous from the chemicals that can be absorbed into the plastic particles over time. It can also block digestive tracts, reduce growth, and it limits reproduction. Let's see here. So my study area will be, how was mentioned, in Indiana, PA's freshwater stream systems. The focal points of these contaminants will be focused in the Indiana Borough Regional Wastewater Treatment Facility, being the town's local sewage treatment plant. The streams and interest will also be Stony Run and Tula Creek. So it's a really bad image here on the top right there. It kind of forks, and so they release the effluent into the streams up there. So my hypothesis of the study is that the increase in population of IUP's campus will lead to the increase in microplastic balloons that will lead into the local water system. The increase is believed to happen with the increase in the town's population during school, for the same reason waste and sewage increases when the students come back to the university after the COVID lockdown. Just more people adding more to the system here. The importance of this study is that the unseen pollution within our environment can cause problems not only to the environment's health, but to ours as well. Still is much unknown of the effects of the microplastic to humans, along with the amount present to Indiana. I believe this is Tula Creek or Stony Run. And I don't know if you can see my cursor, but on the bottom, there's like a blue bag, which I think is plastic. So that's going to be breaking down right next to the wastewater plant. So I thought that was kind of neat. That was just right there. The collection of the microplastics is done by the employees of the wastewater treatment facility. The lab workers present go to the lab building where the effluent can be collected easily with a stainless steel sampler. So on the right, I have the stainless steel kind of cut off, it looks like. And then we have the worker as well. There's like a hatch, and then there's like a door. And I guess they just don't let me do it just in case like liability reasons. But also, if I get time to look at the streams, it will be collected by dipping a glass 1 liter container within the stream slightly below the surface of the water and sealing the container underwater to prevent any floating debris in the atmosphere. So the analysis, the samples would be left in a refrigerator until processing to prevent the growth of bacteria or any other organics. The liter of water will be taken to a sieve stack where the water will be recollected with another liter glass jar. For that reason, we'll be rinsing the microplastics from the sieves and placing it into a filter paper just to hold it to have it organized to be ready to analyze under a microscope. The filter will also be kept under a glass container like a petri dish to prevent microplastics in the room from contaminating the sample. When the sample is dried and ready for analysis, use of a stereoscopic microscope will be ideal while being attached to a monitor to be able to capture images and depict the findings. During analysis, the use of the software will be running to be able to measure the microplastics present. The software will be used will be 𝐒𝐚𝐽. With this, we can determine the longest length and the area of the present polymer just to measure and quantify what's present within that filter paper. So the methodology, the sieves will consist of a 10 to 2 millimeter sieve stack. So the millimeter can be converted into microns, and for example, a 2 millimeter sieve will be a 2000 micron size sieve. Through the process of pouring the collected effluent through the varying sizes of the sieves with different size mesh, will allow the effluent to pass through and be separated by size. Then before that though, we want to do a density separation by adding salt and making an increase in the water salinity to separate the microplastics just from organics or anything else that it could be attached to. So we're just getting the max results there. Density separation will be more of the stream water where organics and more stuff will be present to where it gets stuck to, including sediments. But with it being effluent, it's clean enough for them to put into the stream. Let's see. And then these are just my links for just the images I got for the generic, like these ones here. And were there any questions?
Great. Thank you very much, Gavin. Does anyone have any questions for Gavin about his microplastics project?
I do. Gavin, yeah, I see the different range of meshes you're thinking about doing. Well, maybe that's just a generic photo. I guess my question is, what size do you expect to find? Like, what's the smallest size you'll think you'll be able to collect through this process, through this sieving process? What size, when you're looking for microplastics, it seems like they can come in a pretty wide range. And I believe they can even get down into like the nanometer size. So it seems like you're probably not going to get all of it. But is there like a range that you think is going to be the most common or like that you're targeting?
Yeah, so the most common would be around like 63 microns. So that'll collect like the microplastic size, while the nano will probably go through all that, and that's why we're having the jar underneath, to where if we can develop it even more, we could also just run the effluent through the same way with finer sieves.
Okay, yeah, this is going to be really, really interesting project. Thank you. One final follow-up is when you're collecting your samples, you're collecting it after it's been processed and after it's been decontaminated, or are you processing the effluent prior to the decontamination process at the water plant?
Yeah, so everything's good to go. Like it's right at the end, and they're about to just put it. It's like we cut off the pipe is going right off to the stream, so it's going to be at the end.
Okay, well that's cleaner and more fun to work with, I'm sure.
Yeah.
Thank you.
Yeah, no problem.
Great. Looks like we don't have any questions from YouTube as of yet. And so thank you very much, Gavin. We appreciate, you did a great job on your presentation.
Thank you.
So that's the end of this session then. So we will take a break until 11:55. When we'll come back and we'll have an introduction by Dr. Cercone for the lunchtime session of our 480 students. And so thank you very much to all of our speakers from 470. Great job to everybody in the 470 class. You did a great job today explaining what your projects will be over the next year. And we will get to hear about the finished products over the lunch hour. So we'll see you back here at 11:55.
Okay, welcome everyone. Thank you so much for coming back to join us in this third session of our Geoscience Day. I'm Dr. Karen Rose Cercone, and I had the great pleasure this semester of working with our three seniors who are finishing up their research projects, having started them last year. I don't take any credit for the research. They did that all in conjunction with a specific research mentor. I just help them with formatting and presenting it. And I'm very happy to introduce them today so that they can share what they've learned with all of you. Our first speaker this morning will be Garrett Strittmatter, and he'll be talking to us about research he's done in the Antarctic. Garrett, you can go ahead and unmute and share your screen.
Hello, I'm Garrett Strittmatter, and I'm going to tell you about my research, which was on Scotia sea diatoms and how they relate to climate over the past 30,000 years and why it's the inverse of what we expected. So, with increasing concerns in climate change and sea level rise, understanding as much as we can about climate change or climate science to mediate and hopefully turn back the effects. For those of you who don't know, this image on the right is a diatom. It's a microscopic organism that uses photosynthesis in order to create energy and be productive. They're one of the world's biggest CO2 sinks, which helps us with climate change, pulling the CO2 out of the atmosphere. And they've also been proven in numerous studies to be incredible indicators of their climate conditions. For this study, we looked at a site in the Scotia Sea, which is over here. This is the southern tip of South America, and this is the Antarctic Peninsula. This site is significant because if you look at the right map of currents, there's this Antarctic circumpolar current. And what that does is that takes all of the sea ice and it pushes it into this bottleneck that's created by the southern tip of South America and the Antarctic Peninsula. And that allows the diatoms to settle into the sediment on the seafloor. Here's a more zoomed in map of the site. Again, this green here is the southern tip of South America, and this is the Antarctic Peninsula. Sorry about that. If you look at these three dots here, the site that we looked at in particular was the center site marked April 6th. Sediment cores were collected using a drilling ship like the image on the right that was operated by the International Oceanic Discovery Program, Expedition 382. The sediment cores that were collected look like the image on the left. They're approximately 1 meter to 1.5 meters long, and they're divided into 1 centimeter sections. This is done for two main reasons. The first is so that the core can be divided between different research groups, allowing different research groups to focus on different science. One of the things that came out of that was actually the paleomagnetism that we used to date each of these 1 centimeter slices. If we look at the graph on the right, this is the dating of the core. So as you follow this line down, this is the depth in the core versus the age of the core. For this research, we looked at past 30,000 years. So we were approximately right here. We didn't go very far back. But what that means is that the error bars on the dating of each of these sections is very small. So in order to make the slides that we used to do the counts, what we did was we took 0.05 grams of the sediment from each of the core slices. We put it in an HCl and peroxide bath to take a lot of the carbonates out. And then we placed a cover slip in a beaker and placed that sediment in the water and allowed that sediment to settle down onto the cover slip. The reason for this is it minimizes bias. It gives us the most even spread of the diatoms on the cover slip, giving us the most accurate counts of overall productivity, individual productivity of species, and productivity of the different environmental groups. So when we're looking through the microscope, what we're going to be seeing is something like this left image. This is what we refer to as an FOV, or a field of view. And I'm going to tell you about the four main groups, the four main environment groups of diatoms. So the first group, and what is the coldest group of diatoms, are the sea ice diatoms. The diatom circled in blue is 𝐂𝐴ctinocheilus. It's a very common sea ice diatom. And this group indicates sea ice. So in order for this group to be most productive, it requires the sunlight to be diffused through the sea ice before it gets through to the diatom. So it requires indirect sunlight. The second group of diatoms that we looked at were the open ocean diatoms. They're going to be out in this open water here. This is our middle climate group of diatoms. This one that is circled here in purple is 𝐂𝐫𝐢𝐬𝐿ensis. It is an extremely common diatom. It makes up approximately 50% of the productivity in every time slice at this site. Then the third group that we're going to talk about is the well-mixed group of diatoms. Circled in green here is Styloformis. The well-mixed group of diatoms require extra energy in that water column to keep them on the top of the water column, getting the most direct sunlight that they can. So it's an indicator of how much energy is in the water. And then finally, our fourth group, which sadly isn't represented in this FOV, is the subtropical group of diatoms. The reason it's probably not in this FOV is this FOV shows us a colder climate. This group of diatoms is our warmest climate group of diatoms. They need the most direct sunlight, and they require the highest temperatures. Again, here's our four groups. The sea ice diatoms, that's our coldest group. That's the example I have here is 𝐂𝐴ctinocheilus. Our middle group, the open ocean group of diatoms, represented by 𝐂𝐫𝐢𝐬𝐿ensis, an extremely common diatom in the southern oceans. Our third group, the well-mixed group of diatoms, represented here by Rhizocylenia styloformis. Again, it needs that extra energy to keep it in the water column, get that direct sunlight. And then finally, the group that wasn't represented in the previous slide, the subtropical group of diatoms. This is our warmest group of diatoms. They need that most direct sunlight. They need the warmer temperatures, represented here by Oestropy. So the next three slides are going to be the percentage of the productivity at the site that was made up of each of these groups over thousands of years. So the first one we're going to look at is that open ocean group of diatoms, that middle climate group of diatoms. If you look at the graph, there's very little signal here. And like I said earlier, that's likely due to 𝐂𝐫𝐢𝐬𝐿ensis, the image of the diatom on the right. It's bringing us up to that 50% mark of the productivity in almost every single slide, which is kind of washing out a lot of that signal. What little signal we do have shows us a slight peak here as far back as we went, and a slight peak as we get to current. And that probably indicates an increase in temperature. And then also there's a slight valley in the center here. That is likely a colder period in time. This graph shows both the sea ice group of diatoms and the subtropical group of diatoms. I put them in the same graph for two reasons. The first is there are two most extreme groups of diatoms, sea ice being the coldest group of diatoms, subtropical being the warmest group of diatoms. So as you expect one to peak, you'd expect the other to have a minimum, which we do see here. We have a peak in sea ice here, we have a valley in subtropical here, and that continues as you go back. The other reason is together these diatoms show us the glacial variation at the site. The sea ice peaks are our coldest periods. Our subtropical peaks are our warmest periods. Now, subtropical at this site is never going to be super dominant, and that's just because of how far south the site is. It is a little too cold for them to be a dominant group of diatoms. And then finally, our fourth group of diatoms, the well-mixed group of diatoms. Again, this group requires that extra energy in the water current in order to stay on top of the water column, get that direct sunlight. So what we see in this graph is a loose increase in productivity of these diatoms, meaning that there was probably an increase in the energy in the current. So this graph on the left is the overall productivity of the site over thousands of years. We also like to call that the absolute diatom abundance. So on the y-axis, what we have is the number of individuals per gram of sediment. So as we can see here, as we get closer to current, we have a decrease in productivity. So just keep that in mind. And then looking at this right graph, we have the benthic oxygen isotope 18 graph. So as sea ice is formed, it's pulling water out of the ocean, and it preferentially takes oxygen 16 out of the ocean just due to it being lighter, which leaves more 18 in the water. Now, forams, which are another microfossil, they require oxygen to form their cell walls. And they also prefer that 16, that oxygen 16 to form their cell walls. But whenever sea ice pulls enough of it out, it leaves too much 18 in the water, and forams end up using 18. So what we're able to do with that is the more oxygen 18 that we find in the forams, typically the colder it is. So I have this graph flipped for just for visual purposes, because the higher numbers down here mean colder and the lower numbers mean warmer. So when we look at these graphs, we can see that the warmer is with the lower productivity. So we can say that these temperature and the productivity at this site vary inversely or correlate inversely of one another. Now at other sites, we've seen that productivity correlates directly with temperature, and that's because these are photosynthesizing organisms. They do get that light in order to produce energy. So what that indicates is that at this site there is another driving variable causing the inverse correlation. Now that inverse correlation at this site is likely due to the sea ice thickness at the site or the nutrient availability at the site. In order to confirm this, we would have to look at other sites and see if as we get farther away from this site, if that trend wanes. Or another thing we can do is we can go back farther in the core and look and see if this trend tracks as we go back. Now, if we do find that this trend tracks, that is a concerning trend, because that means with an increase in temperature, there's a decrease in diatom productivity. And with them being one of the biggest CO2 sinks on the planet, it will only compound the effect of climate change. I would like to thank the International Oceanic Discovery Program Expedition 382 for supplying the cores and also for the paleomagnetism data. And I would also like to thank IUP for the use of the facilities and for the use of the lab. And I would also like to thank Dr. Warnock for the assistance with the research. Does anyone have any questions?
Dr. Lewis, you have a question?
Yeah, Garrett, that was great. Thank you very much. That was informative. I have sort of two questions. One is you alluded to the variety that was living in the well mix zone requires energy. Do you mean kinetic energy, like from currents and upwelling, or do you mean sort of metabolic energy?
No, like energy in the currents, just like lifting them so that they're able to float on top of that water column.
Okay. And then the only other question is about the y-axes in your plots. You said the signals were rather small and you didn't have any error bars. Are error bars not a possibility given the types of data, or is that just are they that precise?
Or are you talking about this graph here?
Well, or actually most, and the ones that followed that, you have a point value, but there's no range in any of those values. So are they precisely known with like that?
Well, these points are direct counts.
Okay.
So yeah, I counted approximately 300 individuals in each slide, and then how many FOVs it took to get to that 300 told us how dense the productivity was in that section of the core, and then what percentage of those individuals were made up of each of the diatoms known to be in each of these groups gave us the percentage of the overall productivity of that group of the productivity. Does that make sense?
Yeah, I think so. I appreciate it. It does to many people. I'm a little slow on the uptake here, but thank you.
Mm-hmm. Is there one in the chat?
If you're joining us through the YouTube channel, you can put a question for Garrett in there and we'll read it to him so that he can answer it.
Go back to the question slide.
Garrett, I had a quick question. I think you stated this. I just need a clarification. You were one of the diatom groups was the subtropical species. This seems a little far south for subtropical species. Are these diatoms actively living in the water column where your sample was collected, and so it's a source count, or was it carried by different currents and things like that and deposited? Can you just elaborate on that or reiterate if I missed it?
So the subtropical group, subtropical and subpolar are actually interchangeable terms for this group of diatoms. So they don't need as much direct light, as high of temperatures to be as productive as like a fully tropical group of diatoms. So yeah, they are living at this site. Yes.
Okay, thank you.
Mm-hmm.
We don't seem to have any questions from YouTube today.
Okay.
Okay. So to stay on schedule, we have 2 minutes until our next speaker, and we will let the professors use that time to make notes on their rubrics for our 480 students. To all the professors, if you don't have the abstracts handy, I've asked Andrea to send us the presentation booklet so that we can read them and use them in our rubric rankings as well. Okay, while the faculty figure out how to use their Google document, we're going to move on to our second speaker of the Geos 480 class, and that's Jordan Kulak. He'll be talking to us about an oceanographic study as well, but one that looked a little bit more into the mechanisms of how to analyze it. Jordan, you can share your screen and begin whenever you're ready.
Hello, good afternoon, everyone. I have conducted research on the calcium carbonate content of deep sea sediments since 2019 and will be discussing the results and the merits of each research method. I apologize if my internet cuts out today. It has briefly cut out a couple times earlier today. Hopefully it shouldn't now. Deep sea sediments are a useful proxy for paleoclimate conditions. In the deep ocean, only fine clay, silt, and microfossils are deposited and are rarely disturbed from current flow and bioturbation. The samples I have studied are from the Researcher Ridge in the Mid-Atlantic, collected at Site 10 by the KN-223 Research Vessel NOR expedition in 2014. Calcium carbonate is used to form the shells or tests of microfossils, which are dependent on different paleoclimate and oceanographic conditions. Warmer conditions are conducive to greater microfossil growth, which is recorded as a greater amount of calcium carbonate in the deep sea sediment. Coccolithophores, foraminifera, silt, clay, and other minor amounts of non-calcareous microfossils and minerals comprise deep sea sediments. Coccolithophores are minute photosynthetic algae of about 30 micrometers in diameter. Foraminifera are single-celled protists that consume small organisms or organic matter in the benthic zone, ranging from 10 micrometers to 1 millimeter in diameter. The size difference in microfossils allows for different levels of compaction and percentage of carbonate in each sample. On the left-hand image, foraminifera from one of my thin slides can be identified as the large round shapes with a cross shape inside. Coccolithophores are much smaller and cannot be seen at this same resolution and require a greater resolution to be able to see them. Examples of coccoliths can be seen on the right, either intact or broken. A quick way to determine the carbonate content of samples is to use gamma ray attenuation to determine the bulk density of a sample. Gamma rays are fired at the sediment. The amount that are attenuated or altered are used as an indicator for the density of the whole sample. The bulk density of the sample is then used as a proxy for the carbonate content of the sample, with a greater density indicating a larger percentage of carbonate. However, the bulk density derived from the gamma ray attenuation does not take into account porosity or the microfossil composition of the sediment. Carbonate content derived from GRA bulk density will not be accurate due to these problems. Here, the GRA derived carbonate content is shown as the blue line of results derived, compared to the experimental volumetric gas results in red, with a 95% confidence interval fitting. As gamma ray attenuation bulk density increases, the predicted carbonate content is assumed to increase, while in reality, the results are more complex. order to identify the sources of error for each GRA-derived result, I have conducted volumetric gas and microscope analyses on each sample. The GRA studies were conducted prior to my research by the IODP KN223 expedition. The volumetric gas experiments produce carbonate content results by utilizing carbon dioxide gas as a proxy. The sediment sample that has been pre-dried and had most of its salt removed is ground into fine dust and placed within a vacuum-sealed jar, where it is reacted with diluted hydrochloric acid. The carbon dioxide gas produced by the reaction displaces an equal volume of water in a measurable graduated cylinder. Approximately 245 samples have been studied using the volumetric gas method. Standard calcium carbonate powder samples were conducted each workday to ensure the consistency of results despite daily atmospheric and temperature conditions. The microscope analyses are an approximation of the percentage of coccolithophores, foraminifera, clay, silt, and other components. Different locations of each prepared thin sample are considered first for their fine versus coarse ratio, microfossil versus non-carbonate ratio, then by the percentages of each individual component. Due to time constraints from the coronavirus, the microscope analyses were done in a quick and dirty method that doesn't separate the slides into analyzed sections. 100 samples were analyzed using the microscope method. And this is an example of a petrographic microscope that I used for this study. The samples studied show an increase in GRA density with increased depth, which as expected are reflected as an increase in predicted carbonate with increased depth. The volumetric results also confirm this trend. However, with a large degree of scatter compared to the GRA predicted results. While the predicted results can give an accurate result of the overall trend of the core, it is not accurate for the individual samples, which creates a wide margin of error. The predicted results expect that a greater density coincides with a greater amount of foraminifera, which results in a carbonate percentage between 50 and 60% from least to greatest percentage of forams. However, while the foraminifera composition does increase with GRA density, the carbonate percentage has a much wider range in experimental results. The ratio of microfossils indicates the GRA density and carbonate content. The ratio of microfossils in the studied samples is shown as the volume of forams to coccoliths, with many samples containing more foraminifera by volume than coccoliths. This ratio of microfossils increases with an increased depth of density and carbonate content, indicating that a larger amount of foraminifera increases both conditions. The ratio of microfossils also correlates with the error between the predicted and experimental results. A smaller amount of forams to coccoliths indicates a negative error, where the prediction is greater than the experimental results, while a larger ratio gives a positive error, indicating that the prediction is smaller than the experimental results. Therefore, the GRA predicted results are most accurate when the foraminifera volume is 10 times the coccolithophore volume. At this ratio, the density of the sediment is most consistent with the carbonate content. The carbonate content of each sample is therefore most consistent with the microfossil composition, more consistent than GRA density. Predicted carbonate only references density, losing the influence of the microfossil ratio. Each of the methods utilized for this research are best suited for different purposes. Gamma ray attenuation is best used for studies that require quick results that are only accurate for the average of the core. However, GRA predicted results are inaccurate because of the greater porosity of the upper core not being considered for the bulk density of the core, and the microfossil composition not being known. With these flaws, the GRA method should not be used for studies that require finer scale measurements to be accurate. For studies that require finer scale measurements, the volumetric gas and microscope analyses methods are ideal. The volumetric gas method gives accurate carbonate measurements, and the microscope analyses are best suited for discovering the microfossil composition of each sample. However, both methods are time intensive and require extensive preparation. The volumetric gas method is destructive, and the microscope analyses require extensive training to determine each component. The volumetric gas method also contains an error associated with latent salt comprising part of the sample. The volumetric gas and microscope analyses should be conducted for studies that have ample time and require finer scale results. Future research to better understand deep sea sediment properties should focus on performing more microscope analyses using an in-depth method. During these trials, the identity of non-carbonate minerals and dust should be studied in depth to understand their impact on density and carbonate content. Sieving should also be conducted on each sample to count the size and identity of microfossils and sediment. Lastly, the amount and influence of latent salt on the volumetric gas methods should be studied. I would like to acknowledge Dr. 𝐂𝐚𝐫𝐬𝐿, my advisor for this project, and Dr. Karen Cercone for her guidance with the research project experience, the captain and crew of the research vessel Noor Expedition 223, Grace Wolfslayer and Nathan Birch for their initial work used with the volumetric gas method, and the IUP Geoscience faculty, staff, and fellow students. If you have any questions, feel free to ask them now.
We have time for questions if anyone has them.
Surprised the internet didn't cut out, because it cut out maybe 7 times earlier. Yeah, so.
You held up.
Hey, Jordan, can you pop back to the slide where you had depth on one axis and then your sort of ratio of forams and coccoliths on another one? Yeah. Oh, yep. Yeah. Cool.
This
so
one has carbonate content.
Oh, it's carbonate, not the. Okay. So I guess my question changes a little, but we'll go with it anyways. do you have a feeling for that ratio itself with depth and how that changed through your analysis?
So overall, the GRA density of the core increases with depth, and the GRA density does increase with a greater amount of foraminifera. It's not a perfect relation, but in general, a deeper section of the core for this sample would contain more foraminifera by volume than coccolithophores. Is that the answer you were looking for?
Yeah, that's a good answer. Thank you.
Okay.
Hi, this is Katie, and we do have a question from YouTube. So the question in the YouTube chat is, how deep is deep sea in this study? They're just thinking about the effects of the temperature on carbonates.
That is a good question. Off the top of my head, I cannot remember how deep the sample would be in the ocean. The answer would be the answer would have been included in the study itself. And for my research, I did not look into the effect of temperature on the sediments and the microfossils. So I'm sorry I cannot answer that question.
Any other questions from our audience on YouTube or here in the Zoom session?
Hey, Karen Rose, your microphone is acting very strange.
We'll log out and back in again real quick.
All right, Jordan, thank you. I think there's no more questions for you. And we'll wait for Karen Rose to come back. So thanks for everyone who's on YouTube watching with us as well. It's great to see so many alumni and friends and family and other current students there. So we thank you for that. Karen Rose is just about back in. We'll see if her microphone is working now.
How's that sound? A little better?
Much better, thank you.
That's my internet bandwidth problem, so maybe it's something going on down here in Pittsburgh that affected both Jordan and me. Okay, we're going to give our faculty a couple minutes to stay on time to fill out their rubric scores, and before we conclude with our final student speaker of the GEOS 480 session. Okay, so it's 12:40 and time to pick up with our final GEOS 480 research presentation That's Lauren Donati, and she's going to be talking about her research on Taiwan. So Lauren, feel free to share your screen and unmute and begin when ready.
Hello, my name is Lauren Donati. I am a graduating senior in the Geoscience department. I'm currently studying the rapid exhumation of Taiwan's Eastern Central Range, and today I'll be presenting on the constraints of plastic to brittle structures along the Mugua River. So let's just jump right into this. Taiwan is located approximately 100 miles off the east coast of China. Taiwan's Eastern Central Range here marks the collision between the Luzon volcanic arc and Eurasia's passive margin. Now, while this is understood, Taiwan's deformation history is actually rather complex. There are two competing hypotheses as of late. The first suggesting more of a southward propagating collision of the Philippine Sea Plate into Eurasia's passive margin, while the latter suggesting more of a simultaneous collision of the Philippine Sea Plate into Eurasia's passive margin. As of late, neither of these hypotheses are more governing over Taiwan's deformation history. So with this in mind, we've actually chosen to simplify the constraints and heavily focus on plastic to brittle structures, which are the result of Taiwan's basement being exhumed and the cooling process that occurs then. Again, actually just heavily focusing along the Mugua River, as I've highlighted the location of here on the map to the left. And now I'd like to actually expand on the reasoning for this research. We are able to understand and constrain the deformation history by extrapolating it from outcrops. In the image to the left here, you can actually see a typical field view of our outcrops along the Eastern Central Range. As you can see, the fabric is actually pretty well folded. This actually makes it harder to constrain the geometry and kinematics of plastic and brittle structures. While in the image to the right, this is actually a typical field view of where we collected our hand sample. As you can see, the fabric is actually pretty well preserved and not folded at a centimeter to meter scale. The fabric is actually pretty well preserved between two greenstone units. The bottom of the greenstone unit here pictured, as you can see, while the top of the greenstone unit is not pictured in this image. Now, we've chosen to focus on this sample collected from the Mugua River, again, as the fabrics are not folded at that centimeter to meter scale, thus yielding a more simplified geometry of the plastic and brittle structures so that we can gain that strain geometry from this fabric. Now, not all of the structures along the Mugua River are as well preserved as we saw in that previous sample. We are also focusing on the youngest metamorphic fabric, documented as S3, as well as synkinematic veins and cross-cutting well-developed joint sets. The joint sets are here pictured in the image to the left, while S3 is pictured in the image to the right as a little cyan color in hand sample. So we are inferring that S3 is the oldest of these three structures, i.e. defining the last gasp of the plastic regime, while we are suggesting that the veins are actually documenting the bridge between the plastic to brittle regime. And finally, we are suggesting that our joint sets are documenting the brittle regime. Again, these structures are important because they allow us to extrapolate the deformation history from these outcrops. Now, with previous work, we were able to identify and analyze the principal planes of strain. As you can see in the image to the left, I have labeled our different planes, the XZ defining the maximum extension direction, while the YZ is defining the intermediate, and the XY plane is defining the finite shortening plane. Now, these planes were determined by the perlite class that we can see here in our image to the left. We could also see these perlite class in our outcrop as well. Now, our previous method that we used for this analysis was not very efficient, but we were able to analyze the axial ratio of the classes in thin section in a size order. So we went from large class, medium, and small in thin section. And now, before I go into the results of this analysis, I'm going to explain the RFI plots that you can see over here to the right. I'm going to be using these plots in our past method and our newer method. So I'm going to explain what these values mean. Along the y-axis, the R value is indicating the axial ratio, which is just the medium radius over the minimum of these clasts. In our previous method, what we did was we digitized each clast by hand. Obviously, this is very time consuming. Now, the results yielded that in our medium clasts, the R value here is actually lower than our YZ. So this is interesting because this does not support the principal planes of strain that we had previously established. Now, what I'd like to do is explain our newer method, which was thus supported by our previous analysis, which is why we wanted to examine these medium grains which in our matrix. So we used an application called Strabo tool. In this application, it's much quicker and more accurate analysis of the axial ratio of the clasts. So this is just an example of what Strabo tool would typically yield. In my analysis, I created small subset images of our thin sections looking simply at the matrix. And as you can see, it just yields an axial ratio value for these images. Now, to display this, as I mentioned, I will be using RFI plots. I use the application EllipseFit to create these RFI plots. I also used StaringNet 10 to visualize and put our plastic brittle structures as well as our principal planes of strain into that geographic context. Here in this image, you can actually see our principal planes of strain put onto a StaringNet to add the geographic context of these planes. So now I'd like to go over some of the results from this analysis. As you can see here, our XZ plane and our YZ plane yielded a mean R value of roughly 1.6, while our XY plane yielded a value of about 0.8. All right, and then additionally, our plastic and brittle structures here, as you can see, S3 appears to be gently dipping towards the north-northwest, moving to our transitional state of veins. You can obviously see that they're dipping almost nearly vertical towards the northwest southeast, while joints appear to be doing the same. Here, obviously, we plotted the poles of these planes for just a simpler view of the data. So now in the next slides, I'm going to be going over what these results actually mean. So if you recall back to our original slide, we saw that in hand sample and in thin section, the clasts appeared very prolate, so very cigar shaped. However, in our matrix along our XY and YZ planes, our mean R values are actually rather similar, coming in at 1.6. This actually does not support that we see prolate clasts in our matrix, but oblate clasts. So we see where these matrix is experiencing more of a three-dimensional flattening strain, while we suspect that outside of the matrix, there's more of a plane strain, two-dimensional flattening happening in this outcrop. Moving on from there, as I mentioned, S3 appears to be gently dipping. This suggests that it may have formed relatively late during rock exhumation, thus supporting that this fabric is the youngest of the metamorphic fabrics. Finally, we then infer that S3, as I mentioned, is the oldest of these three fabrics and appears to be coeval with the veins with which we see or observe a mutual cross-cutting. Now, additionally, in that same preserved outcrop that our hand sample came from, we identified this spaced foliation within a phyllite layer. We hypothesize that this spaced foliation is actually possibly S3. As you can see in the StaringNet to the left, the red line is actually plotted of the attitude of this spaced foliation along with S3 from this river. As you can see, as I mentioned, the attitude of these two different structures are rather similar. Now, while we cannot record this phyllite interbed as S3, it does suggest that the flattening strain that was recorded in the matrix of our previous sample is possibly or is synchronous with the formation of S3. So now I'd like to summarize what I've just suggested. So my work suggests that the fabrics parallel to S3 in this well-preserved outcrop might tell us that during the formation of S3, the strain field is experiencing more of a three-dimensional flattening strain. An inference that we can then make is that during exhumation in the plastic regime, there was more of a three-dimensional flattening strain occurring, while during the brittle overprinting, it was dominated by more of a plane strain and thus additional with northeast-southwest extension. Now we're suggesting that our outcrop is located approximately at this border, and we hypothesize that an excuse for this interesting strain occurring here is that there could possibly be an exhumation of a high pressure metamorphic unit being exhumed from below, imposing more of a subvertical shortening in this low pressure rock. Now, with future work, we could go on to identify more of this plastic three-dimensional strain that we were talking about previous. As you can see here in the image to the left, these are all locations that we have previously visited that we have collected data from already. So there's plenty of additional research that can go on along these outcrops or along these river outcrops. Now, I would like to thank Dr. John Lewis and Dr. Karen Cercone for their research discussion and formatting assistance with my poster and my presentation today. I'd additionally like to thank Copeland Cromwell and Lindsay Almond for their assistance with the GMT software, as it was very helpful during our initial analysis of Taiwan. I'd also, of course, like to thank Susie Adams and the past and future members of Team Tecto for making this research so enjoyable. And of course, I'd like to thank the NSF for funding this research. Now, if anyone has any questions, now would be the time to ask.
We have time for several questions if anyone would like to ask Lauren about her research. Lauren, I have a question for you. Was there anything that particularly surprised you about your findings, or did they fit in with what you had previously known about the tectonics there?
So I would definitely say that, sorry, I have to go back. I would definitely say that the more oblate strain that we saw here, or the perlite class, was actually very surprising. As I mentioned, we only expected to see more perlite strain here. So it's interesting to see that in this outcrop, or in the matrix, in these smaller grains, that we see a different strain occurring. So that's why we ended up hypothesizing, or trying to hypothesize why this was occurring, and why we used that example of a high pressure metamorphic rock unit being exhumed near our river outcrop.
Giving the folks on our YouTube channel some time to post questions if they have them.
Yeah, so here's a question from YouTube. What are the skills you've learned from this project that you will be able to use in your graduate studies?
So I would definitely say that this process was very tedious, especially our first method that we used, where I had to by hand digitize each class. So I definitely say that this has taught me that while the process might be very tedious, the results can be very beneficial, as that initial analysis that I had mentioned here, had yielded that we needed to do further analysis into that matrix. So obviously it's very beneficial, even if it's a tedious amount of work, is what I learned from my research here.
Great, thank you. I'd also like to note that there has been an accusation on YouTube that that was a planted question.
Can I ask who asked that?
Dr. Deardorff, but Lindsay's the one who asked the original question, and she did fess up that it was not planted.
Just teasing, of course. Well answered.
Okay. Any other questions coming in, Katie?
No.
Okay. Well, I would like to thank again all three of the students in GEOS 480. They supported each other throughout this entire semester and were one of the best classes I've ever had the pleasure of working with. So congratulations to all of you and best of luck on all of your future endeavors. I'm going to turn it back over to Katie to explain the rest of today's events.
Great. So thanks everybody so far, all the student speakers, you've done a wonderful job. I feel bad that we weren't able to have applause for you, but you did a fabulous job. So we're gonna go into another break here until 1:10, and then we will have our keynote speakers from the U.S. Geological Surveys, Pacific Coastal and Marine Center from the U.S. GS in Santa Cruz. So we'll be back in 15 minutes or so. All right, we're just about to get started again. There are our speakers. All right, I think everything is set up to go. Karen Rose, did you have anything else to say? Okay. So welcome back. We are now preparing for our keynote speakers, and it's my distinct pleasure and definitely also my honor to introduce our two speakers today, who I figured out I've known both of them for over 2 decades, which is pretty shocking, through multiple different institutions that we have all worked at as our careers have evolved over the past 2 decades. The first to introduce is Jerry Hatcher. He's an IUP alum. I think his actual degree was in applied mathematics, but ever since I've arrived here, I've decided he's a geoscience alum. He comes from the Clearfield area, and he's been kind enough many times to stop by and give me a hand with some of our equipment. As a student here at IUP, he took oceanography with Paul Prince, and that was what set him on his I want to say quest, but that's not the right word, on his career path into ocean engineering. And he currently, as I said before, works at the U.S. Geological Survey in Santa Cruz, California. I think you got your degree at the University of Rhode Island, your ocean engineering degree. Is that correct, Jerry? Great, thanks. And anyone who's ever worked with Jerry knows that he's really MacGyver, because not only can he create anything that you need, but he can do it on a ship in the middle of the ocean when suddenly something goes wrong. So he's a great person to have on your team, without a doubt. Our second speaker, we're doing a dual keynote speaker. They're going to be speaking together. I've been informed every other word. No, I'm kidding. But they're going to be giving this talk together is John Warwick. And he is a coastal geologist who works on coastal watersheds and coastal shorelines in the near shore, and looking at the interaction between the terrestrial and the marine environment and how those are linked closely together. His educational background is he got his bachelor's degree at Cal Poly, spent some time away from California, which not many Californians like to do, in Wisconsin for a master's degree, and then back to UC Santa Barbara, which is where I met him for his PhD work. And he is also currently at the USGS in Santa Cruz as well. And they're going to be talking today about sort of the teamwork that is needed to produce great marine and coastal science, and the variety of sort of career opportunities that you might not know exist in those fields. So I'll turn it over to the two of you.
Okay, I'm going to start it off. And first I want to say thanks for having us, Katie. This is great. And it's a really an incredible honor and cool experience to be able to talk to, you know, my old place of origin. And we're going to talk about some of the fun and interesting projects I've been able to, been fortunate enough to work on since coming from IUP here at USGS. And it's also such a cool small world experience that we met out here, and now you're at IUP as a professor, and I'm out here at USGS still. It's changing places across the country, so all that's really great. And with that, we'll share my screen. Start the. Oh, and I want to thank John for putting this whole PowerPoint together. I have been crazy busy trying to put, and he's just as busy as me, but he's got more bandwidth somehow. We're leaving for field work in another next Wednesday, so I've been packing and shipping and getting things ready, and so he pretty much put this whole thing together. So with that, let's see if this goes.
We're going to Key West, so
yeah, it's not bad field work.
Yeah, right.
All right, so can you guys, everybody see that?
Yeah, it looks great.
Okay. Trying to put it in slideshow mode. Oh, nuts. Okay,
Yeah,
hold on.
that kicked out your screen sharing somehow.
Yeah, let me try again. Sorry about that.
It's okay. The government doesn't let you use Zoom, and so we've all been using it for a year, and it's new for you, so no worries.
Is it okay there? How's that look?
That looks great.
Okay, sorry about that. All right, so what we're going to talk about today is a small part of just a small wedge of the whole pie of a giant arching project shared between our three centers. We have a center in California, one in Woods Hole, and one in St. Petersburg that all deal with different chunks of the coastal United States. Let's see. The outline of our talk here is going to be, we'll talk about the working model, how John and I have worked together over the past at least decade, and how we've kind of come to share responsibilities in a way that ends up being super productive and super fun. And we've done a lot of really great things. Then John will pick up and describe a little bit about how we've been using photogrammetry with structure for motion and imagery in general. And John is the principal for the entire project, so he stays more in sort of the overreaching big picture items or a view of things, and I get to spend my time digging down into the minutia of millivolts, microseconds, and that sort of stuff, trying to improve some of the equipment and ways we do things. And then we'll describe 4 of the projects. These are just 4 of many projects in a little more detail for you guys. And then John will wrap it up. The main thing to start off with is this is definitely a village. None of this stuff gets done in a vacuum. There's a whole team of people with all different kinds of experience and backgrounds. And when you put people like that together, you can do things that's definitely greater than the sum of it all is greater than individual pieces for sure, because everybody brings a different perspective and has ideas and throws things together in a way that you don't expect. Like I said, this is one part of a remote sensing coastal change umbrella project that I work on. I spend a lot of my time in the evaluating new remote sensing technologies, innovation, and applying the technology towards things. And John spends more of his time maybe over in this side, but we definitely have overlapping interest and experience, but focus in different areas, and that makes the whole thing more productive. So our working model, how we usually do things is John will, as being the manager of the entire project, has his fingers on all the different aspects of what people are doing and identifies the different problems. People come up with things they want to try to do. And then we develop a technological approach to try to figure out how to solve some of these problems or investigate issues. We test these solutions and apply them in the field. And then based on what we learn from that, it circles back around. And although this diagram's written to kind of circle around this way, it doesn't always go in this sometimes it goes back and forth. As an example, we might develop something based on a direction we're trying to go. And when we develop it, we realize that we can do something else that enables us to investigate a problem we didn't realize we had the ability to investigate. So it doesn't always go in this nice circular fashion. Things cross back and forth, but in general, this is the flow. And so with that, I will turn it over to John.
Perfect. So one of the technologies we've been utilizing has been structure from motion photogrammetry. And I don't know if you are teaching that at the university or not, but it's sort of this new technique that's been developed over the last decade, and it's based on centuries old techniques of surveying and several decade old photogrammetry properties and principles. But there's sort of this new wonderful technologies that have been developed to basically map the world, anything in the world that you like, at scales that you're interested in by just basically using a camera. And so the picture on the left shows my very first structure from motion photogrammetry project. It's a rock on the beach in the central coast of California, and I just used my iPhone to take 7 or 8 photos and built that 3D model. And we've been really fortunate in the USGS to have experts in this technique, Nefer Matthews and Tommy Noble, who are shown there on the report on the right. They've provided a lot of expertise in helping us develop some of our techniques. And so one of the really neat things is that we've taken this new technology and we've really been trying to push it. And I hopefully you'll see that in a lot of the projects we'll show. So next slide, Jerry. So just as a reminder, here we've gone over the introduction, kind of described how we work, and I wanted to describe very quickly what that photogrammetry technique is. And in a sense, it's building 3D models of things, digital models, using photos. And now we're going to jump into these example projects, and we'll sort of alternate, as you see. I think I'll do the first one, the plane cam, and then we'll jump back and forth until we get to the conclusions. Okay, Jerry? Perfect. So when we got interested in photogrammetry and the fact that we could maybe start mapping using photos, we went out and looked for photo sets that existed. And in California, we have this wonderful program called the California Coastal Records Project. It was started by Gabrielle and Kenneth Adelman. You can see them there next to their helicopter. And Gabrielle flies the helicopter, and Ken sticks his head out and takes pictures of the coast. And they've done this several times over the last couple decades. And so we thought, hey, here's some photos. Could they work? And it turns out, thank you, Jerry, that they worked really well in mapping the coast. They weren't perfect. There are some challenges in using them, but as a first try, we were really blown away. And this shows, you see the panels there in the middle. On the left panel are some of the raw photographs. This is of an area of the Central Coast right by San Francisco. It's called Fort Funston. It's part of the Golden Gate National Recreation Area. And so those raw photos, you can see there is a landslide. I think you can maybe see that in the photos. In the middle column, that's the 3D model. We call it a point cloud because there's a bunch of points out in 3D space. And you can see that that's what we've generated from those photos. And then in the right, you can see a difference map. So it's a difference between the various survey years, and red is erosion and blue is accretion. So you can see in the uppermost panel, you see the erosion of that landslide. And then with time, you can see more erosion occurring, mostly at the base of the landslide. So this was like eye-opening. So what did we do? Well, Jerry and I started talking, and next slide, we thought, gosh, wouldn't it be great to collect our own imagery when we wanted to, one, and wouldn't it be great to improve upon these techniques primarily by introducing accurate positioning? That is, if we knew where that camera was as it was flying along the coast, we could actually build better models. We knew this from a couple of examples. And so Jerry and I and a couple other folks in our center started thinking about how we could do this. And so what has resulted is what we call plane cam, and that's Jerry standing in front of the plane cam. And the key elements to it there's a number of elements to it, but the key elements are that there's a camera. You can see that Nikon camera, and that's looking out a little window in an airplane door. Yeah, thanks, Jer. And then it's synced up with the GPS. So you can see there's a GPS antenna and it's called a Trimble R7 GPS. So those two units are synced up in a way that we accurately record the positions of each photo. And I'll note that Jerry is standing in front of the yellow thing behind him. That's an underwater sled, one of his earlier underwater sleds, and we're going to go back underwater by the end of the talk. We'll get there in a second. Okay, next. So we started flying this along the coast, and this kind of shows some maps of where we've been flying over the last couple of years. We fly along the Central Coast. We collect thousands of photos, and from that we can build 3D models. And on the right it shows sort of how that system fits into the airplane that we contract. There's a system outside of it, and then once you get it all inside the camera's looking out that window. So next slide. The cool thing is it creates wonderful 3D. We can create wonderful 3D maps. This is an example of some bluffs in southern Monterey Bay. You can see the erosion processes, and there's actually some concrete on the coast there, and the parking lot on the top of the bluff, etc. So we could really see a lot of wonderful things in these data and collect them fairly easily and process them fairly easily. One of the coolest things we did with this so far, and next slide, was look at the Big Sur coastline, and we were able to collect imagery in 2017 leading up to a massive landslide that closed Highway 1 for over a year and required almost $300 million to reconstruct. And this is the day before the landslide. You can actually see with your eye that the highway doesn't exist anymore. If you look along the central part of that 3D cloud, I think you can see the highway corridor is kind of gets it's actually in the ocean right now. And because the next day something happened, and Jerry, if you toggle, this happened. This is the Mud Creek landslide. Of course, this was a really wet year and it saturated the materials, and it wasn't until the early summer in May when this failed. So if you go to the next slide, the cool thing was that we worked with Caltrans with that data, and we were also able to sort of track changes after the landslide. So we provided them data before and provided them data after. And so if you go to the next two slides, you can see that this just shows a 2-week period showing how much change had occurred over those 2 weeks. So we kept on monitoring this slide over time. You can see up there in the orange on the upper portion of the scarp, there's erosion, and blue is accretion. So there's a lot of material still sort of coming down off that landslide scarp. Next, Jerry. And then this just shows a time series, a 3D model of that landslide sort of before and after. And if you're interested in this, we have all the data we're publishing. You could use it in your classes, or you could use it in a project. But again, this is just one of the examples of what we could do with that new plane cam and some of the science and monitoring that came out of it. Okay, Jerry.
All right, so based on the timing, so in order to make John alluded to the fact that we need to be able to tell exactly where those pictures were taken in order to get a better model of the terrain below. You can either do that by putting out a lot more ground control or knowing where the camera is a lot more precisely. But if you're in a plane that's flying along at around 100 miles an hour, things happen really fast. You're traveling at the order of 150 feet per second at 100 miles an hour. So microseconds matter when you're trying to measure things into the meter or less. So I spent a lot of time doing experiments, figuring out what the delay is between when you actually push the remote shutter release button on the remote shutter release that makes the camera take photos, and when the actual photo is taken by taking pictures of lights blinking really fast at high shutter speeds and all that sort of thing. And also testing between multiple cameras what kind of variability there is, because we needed to have a spare system in case that. No, sorry, sorry, I got interrupted there. Just as sort of happenstance, I was testing multiple cameras, and then we had the idea of, hey, what about the possibility of, rather than moving the camera through a scene, so okay, let me back up a second. A lot of times when you're flying the plane, or all the time when you're flying the plane through the scene or taking structure from motion, anything that moves, it's not stationary, while you're moving the camera has to be sort of eliminated from the data set because it's just blurred between photos. While I was doing this, we had the thought of, okay, what about taking multiple angles simultaneously and capturing things that are in motion from different angles at that instance? And then what if we could take it down to the ocean and measure the sea surface with that? And another thing that is shown in this picture right here is this more traditional way of measuring things in 3D, which on the train, which is a LiDAR, which is a laser ranging instrument. They don't work very well in the water. The water reflects them. They can only take a strip of data real quickly and not a whole scene. So the camera is, if this worked, it was going to do some pretty interesting stuff. So we took it down to the coast. I set up the 3 cameras. I was using radio receivers between them to trigger them all at once. Just gave it a go. We just happened to have a really good day where there's a lot of whitewash on the surface and some good waves. And what you're seeing here is the scene from the 3 cameras taken simultaneously. So this is a zoom in of this particular wave crest right here. And you can kind of get verification that by looking at just this little lip of a wave or these shapes right here, that we're really nailing the time synchronization here. And so we took these 3 photos, put them into the structure from motion software, and lo and behold, it worked. I was in my office and John calls me up and said, hey, this stuff worked really good. You got to come over here and see this. And I was just kind of blown away by how cool it was. But John, being the big picture guy, was blown away by how we could apply this in a whole ton of different ways and get a whole wave field where before it was just 1 or 2 point measurements of pressure. Now we had an entire matrix of the sea surface, and the implications for civil engineering and looking at coastal erosion that were really huge. So the next thing we did was took it out to a bigger, an area where we've been doing some studying of wave beach processes over seasonal change and that sort of thing, to try to see if we could capture a wave train and over a bit larger area. So this is just about 10 miles down, not even 5 miles down the road from where our office is. There's a nice bluff there where another project that you'll hear about from John in a minute was already kind of in place looking at time series of waves. We kind of scaled the system up a little bit by separating the cameras and looking at a bigger area and mess with the lenses and so forth. Same radio controllers, capturing a series of waves over a long period of time. This is an example of the 3 cameras views of the same overlapping area. And one thing I want to point out is, and these are 2 time frames a second apart. So this is left, center, and right camera. There's a person right there. Hopefully you guys can see this in the video or the screen sharing. And then this is down here's 1 second later. And let's see what you see, maybe this little point right here, the wave closes out, so there's a little bit of change. And when you put this all together over time, you get a 3D model that traverses time. And then right here, notice that that's that person walking down the beach. These are the waves. We're looking at it sideways here. So the cameras were up here to the left. So this is looking out offshore here. So it's a little disorienting, but that's the best way we could plot it. But you're looking at the wave trains come in over time. You get to see all this really cool reflection and different ways that the waves come in. So this is for physical oceanography and looking at the way that sediment gets moved around. This is like a gold mine of data right here. Huge volumes of data, but really amazing stuff. So this encouraged us to keep going further with this kind of thing. So then we got into a collaboration with, again, the takes a village kind of thing. We're showing it to people around the office. And one of the other researchers here who's a graduate of the Naval Postgraduate School and working with one of the researchers down there knew that they were interested in figuring out how rough seashore changes the flow dynamics over a tide cycle of waves. So we went down. We went down with the intention of making these models every second or minute. I remember the exact time. This has been a year or two. But anyhow, over a whole entire tide cycle. So we went out down there and set this stuff all up and made a whole bunch of models over time as the wave came in this little inlet here. So we had cameras up all around here and made a 3D model of this. And this is just some of the pictures of this going on. And that data is all still being worked on. And then this is the long time series coastal cam stuff I alluded to earlier that John's going to talk about.
Perfect. So there has been a history of setting up cameras and in a stationary manner and watching the coast evolve over time. And some of you may know of that work. It was termed Argus, and we've been very interested in using those type of data and collecting our own data. And so here's Jerry and another one of our colleagues, Sean Harrison, who was a postdoc at the time. And Sean's postdoc work was focused on doing these types of measurements using fixed cameras to sort of look over longer intervals of time, months, years. And so they developed this kind of new station, which was cool because it had cameras in them. These are heat shields, so they don't heat up. One of the neat things is in exploring cameras, there's all kinds of new cameras, and that became really relevant to this, but also the next underwater system we're going to show you. And also, with microprocessors getting so small, they could do a lot of the processing of this imagery in-house, so you didn't have to ship so much data off. We collect a lot of imagery over time, and then there's a lot of averaging and other types of things that are done with them. So that this is sort of a neat combination of processing and of course communications. It sends data, and then the cameras themselves. Okay, Jared, next slide. So here's an example of what you can do with that. What's really neat is you can take these raw images. There's 2 cameras on this system, and again, it's at the same site here in Monterey Bay that Jerry had talked about, showed that those wave fields before. And so you can use these raw images to produce a map. And so if you rectify them, if you know about the spacing, so you need to get out here and collect some survey data. But then what's really neat about that is you can then create what's shown in that sort of lower right panel is that merged, 2-camera perspective of, it's basically a map of that site. And if you go to the next one, Jerry. And what's really cool is you can do lots of cool stuff with that. And so we had the pleasure to work with Mia Pavlock down at Moss Landing Marine Lab. And she wrote her thesis on the data we're collecting. So she collaborated with us and did a lot of really cool processing of the data. And one of the things she was looking at is, where does the shoreline exist in these data that's shown on the left? And then where are the offshore bars? And so the offshore bars are where the waves break. And then she was wondering how those vary in time and how they're related to waves and all kinds of interesting questions like that. Next slide. So, and these just show some of her data. So what's shown here are almost 2 years of data. The lower plot shows wave height, and you can see in Monterey Bay, the waves generally get bigger in the winter and they're smaller in the summer. And so one of the neat things is you can see the position of the shoreline in the upper plot and the position of the sandbar, the offshore bar. And so what's neat is that during the winter time, if you look at the sandbar first, the sandbar sort of creeps offshore through the winter, and then it comes back onshore during the summer. Whereas the shoreline does sort of the opposite. The shoreline gets eroded back, you can see in that first event in January 2018 that you see the shoreline eroded back 34 or so meters. Yeah, right in there. And then it sort of crept back out during the remainder of the year, and then eroded back much more in the subsequent winter. So again, this is some of the data that Mia put together using this type of a station. And I think that might be it for this section, Jerry. Oh no, there's a little machine learning. Oh, we also use this and I don't know if folks are getting interested in artificial intelligence and machine learning, but this provided a wonderful data set to try out some of these techniques. And the fundamental idea is that, you know, you have these complex computer systems that can evaluate patterns in imagery using machine learning, and so we knew from our raw imagery, if you look at the top plot, you can see, you know, if your brain would say, yeah, on the left there's sort of small waves, and as you move to the right, the waves are getting bigger, right? And then on the and also in the bottom plot, you can see, I don't know if you can see the wave crests, but they're sort of stacked up on top of each other on the left-hand side, and they're much more broadly pulled apart on the right-hand side. And that's related to the wave period. Wave period is short on the left and longer on the right. And so we wondered if machine learning could use these images and actually measure those things. And if it could, we would call that optical wave gauging. And the coolest thing is, the next slide, is it worked incredibly well. And this just shows some of the data that were generated. These are time series, so this shows with time measurements offshore of waves using an ADZ piece, and then in red it shows our optical, our image-based estimates of wave height and wave period. And again, we were pretty blown away by these results, and it's allowed us to, now we're taking this and starting to apply it to, we have these cameras now set up all over, and we're going to be developing more, and we're excited about trying these techniques out with those. So that's, I think, the end of this section. So I think, Jerry, you're next.
All right, so the final project we're going to talk about is sort of combines a lot of this previous work and experience. And it resulted from, again, this is a broader umbrella project, coastal and erosion and protection and stuff around the US. The Florida people from people from the Florida office had a camera system they had used to pull around and collect video at depth of coral reefs to do habitat mapping and assessments and so forth. Their system was using standard definition, needed updating. And as John pointed out earlier, I have made a bunch of different camera systems in the past. And so they approached us as they were under the umbrella project of, you know, again, takes a village, talk to people that know what's going on about potentially updating their system. And based on all the work we had done, we kind of thought, hey, this might be a great opportunity to try out the idea of underwater structure from motion, which would be way more quantitative than just the video, and really bring it to the next level. And this, like I said, alluded to, this sort of took all of the tricks we had learned over the years and put them all together. So we've got multiple cameras aligned relative to each other. You can see this one's tilted back, that one's tilted forward. These floats, as you can see in the picture here on the right, keep the vehicle on the surface, but the cameras are submerged so they don't get pictures of bubbles and stuff while you drag it through the waves. And the cameras, I spent a lot of time making sure, we realized that from our previous work that the lenses and the distortions and all that really matter. So when you're trying to get down to the best you can do, you got to pay attention to all this stuff. So the mount, this is one of the machine vision cameras that we learned about doing the Argos project. They're really great for their small size and symmetry, which makes them really easy to mount centered in the middle of a lens. And all this together, we created the SQUID vehicle, which is this structure from motion quantitative underwater imaging device with 5 cameras. There's nothing magic about 5 cameras. You only really need 3, but we wanted to make sure we had plenty of data and overlap, because when you are towing a vehicle on the sea surface, it's bobbing around and the cameras are pointing all over the place. So we figured it better to get too much data. You can always throw it away than not get enough and not get enough overlapping photos. So we took the whole thing, we did a bunch of testing out in the parking lot first, made sure that the concept worked. Built the vehicle. There was a couple of misfires there. We had, like I said, this puts the cameras down deep in the water so that they don't see bubbles and stuff. That was one of the mistakes of the first system. The first float I made is it got way too much bubbles. It floated too high. Had to make this thing so it could be shipped across the country, fit on the boat we were going to use with our Florida folks. Took it to Florida to give it a real test in the field. As you can see, I'm looking at this is our test tank. I was checking the buoyancy, having some fun out there in the tank. This is the boat actually in Florida, us deploying it. We didn't really have any kind of goal other than to see if it really worked in the coral environment and that we could deploy it and collect some usable data. This all recently got published. This was I was actually able to use the kind of the off time with COVID to push this paper through, and so it's actually described in huge detail in this publication on Frontiers in Marine Science. So if you want to see it, just look for SQUID 5 Frontiers in Marine Science, and it'll show up in Google. So the way this thing works is with the 5 cameras, each one of these, this is an example of the seafloor model that got created. There's some sand waves there. This is a little bit of an old reef. We just, on this venture, we weren't trying to map any larger areas. We were just trying to kind of drift over some areas where we knew we had some targets and things we could image, just to see how it worked. And the way that it goes is you move through the scene, taking pictures that are synchronized. All 5 of these cameras take pictures at exactly the same time, and they stamp a really precise event mark in the GPS stream. So we know exactly where the antenna is. We know exactly where all the cameras are relative to that antenna, because these lever arms are all fixed. And because of that, as the thing moves through down this line, there's only one solution where all 5 of these features, or all 5 of these cameras, can match features that they see on the seafloor with where they know the antenna is and where their relative position is to each other. So the magic of that is, without any kind of compass or heading sensor or tilt sensor or anything, we can create georeferenced surfaces of the seafloor with incredible detail and amazing accuracy. We were kind of blown away by this. And so this is an example of what you can use this for and how good it is. We went out and repeat surveyed the same general area. Like I say, we weren't doing a survey line, so the areas don't exactly overlap, but enough of it overlapped from day 1 to day 2 that we could compare things. And what immediately comes out, of course, is how this sand wave ripple field realigned itself completely over one night, and it changed everything. The way we used to measure this is just by putting down a little arm and doing little point measurements along a 2-meter arm. Now we have the entire field. And not only do we have that entire field, if you take a few points that you know didn't move, such as rocks or some reefs, you can really nail this thing down between days to where you can measure, shown here on the right, millimeter kind of offsets. So this is just incredible precision and accuracy. And what we're getting at here is you don't have to survey those points in. You just have to know they haven't changed. So you don't have to do any kind of laborious surveying the points in, because we've got the positions from the GPS that's on the vehicle. In addition to creating just that beautiful topographic map of the seabed, we get the associated full color photographs that go with it. And those also get aligned and orthomosaicked to be precisely laying on top of this stuff. So now, not only do you have that crazy accurate bathymetry, you've got the color information to go with it that can be used by biologists and so forth to really get a handle on what kind of species are out there, how good they look, as far as health, and then we can do repeat surveys over time to check on coral growth or decay. And that's why the coral reef people are really excited about this. And that's why we're going back down there next Wednesday to do an actual survey where they're replanting some of these reef areas to see if they can establish communities again where they're having some trouble with climate change and human impacts and so forth, because the coral reefs are such an important environment to protect the seashore and provide, of course, recreation, that sort of thing. But they're an incredibly valuable resource that's in kind of danger right now. So this is a really amazing tool. People have been out there doing this with scuba and just handheld cameras and stuff, but they don't get the georeferenced repeatability that we've been able to achieve with this vehicle. So that was our first experiment. We came back with a whole notebook full of things that we needed to improve and ideas to make it better. Got sidelined from COVID, not going back down there last year, but used that to refine those improvements and so forth and techniques a little further. And then before we went back down to Florida and spent all the time shipping everything there on getting all this down there, we wanted to make sure that the thing worked. So we used the sideline COVID time to go to a local lake, Lake Tahoe, which just happens to have a famously clear water. And we were able to partner with, again, it takes a village kind of thing, partner with some folks at the UC Davis that have a boat up there that they use to monitor water clarity and mysis shrimp invasions and that sort of stuff. And they happen to know exactly where the perfect analogous kind of formations were to a coral reef in just the perfect depth of water, and took us out there. It happened to be March and snowy, so we got to work in the snow with the vehicle instead of the tropics, so that was interesting. And tried to run lines and map an area that was pretty much analogous to the kind of area that a coral reef would use, which is 300 meters by 250 meters as a good chunk. So we did this in just 1.5 days. It's about a terabyte of data. The data volume is huge. So we're pushing the limits, not only in the technology, but just in data transfer and computer speed. It takes 6 to 24 hours to process some of this data sometimes. Got really great full resolution coverage. This is the bathymetric map. This is a lahar formation. It's a volcanic, kind of soft volcanic that gets eroded over time. So it is really super interesting and cool. We were expecting to just kind of go up and image a bunch of logs and rocks and so forth, but this was way better than anything we expected. And I'm going to zoom in right on this little area right here so you can see kind of the resolution we're getting. So again, it's this little nub right there. Look at the scale we've got. So we've gone down to 2 meters, and the stuff that we can see in this is the associated imagery, is just kind of blowing us away. And so this is, for the coral reef scientists, this is gold. This is a gold mine here. So like I said, we're going back down next week, going to try to collect a similar size area, actually twice that size area, off the Key West area for Eastern Dry Rocks Reef, which is one of the NOAA iconic reef replenishment areas. There's a whole bunch of that kind of effort going on down there. So we're hoping to play a big part in that over the upcoming years. And with that, I'll turn it back to John for.
Perfect. Well, I'll bring it home. And over the pandemic, I have been doing some reading, and one of the books that I read was Jared Diamond's Guns, Germs, and Steel, which is obviously tracks sort of human history. You probably know it reasonably well. I really enjoyed the discussion of technology development in that book, and the conclusion that, and I found the quote that he quotes, he writes, technology develops cumulatively rather than in isolated heroic acts. Technology develops cumulatively rather than isolated heroic acts. And I think what is suggested by that is that how I interpret that is that advances in technology occur by these incremental improvements that are that contributed by many people, that all of us sort of who are working in this sort of contribute and make these incremental improvements, rather than, and Jared specifically talks about this, there's not just a few geniuses that matter. It's actually all these folks who are working on this together. So Jerry, if you hit next slide, I'd say that thought is entirely consistent with our experiences, in that that the collaboration and working together is really key to our success. That you know, we certainly couldn't do all this working alone. And when we are in the lab together, in the field together, these new ideas come, and then we can test them and try them out, and various expertise and interests can be applied to them, etc. And I'd also say it's a key to the fun and the real enjoyment we get out of our work. And I'm really thankful for that. I'm thankful for being able to work with Jerry and the cast of folks you see here. And on that note, I'll say thank you for both of us. This was truly an honor. Thanks for having us.
Great. Thank you guys so much. And we'll open it up for questions. That was mind-blowing, by the way.
Thanks, Katie. Like Jerry said, our minds have been blown along the way. We thought, oh, let's try this out, and then it was better than we expected, which is like, when does that happen? Never, right?
Yeah.
So it's happened a few times.
You all had talked about, you know, how amazing it was, but I hadn't spent the time looking into what you had come up with yet. And that was amazing.
So I've got too many questions to really throw out all at once. So I'm just going to start off real simply. And I see John's already got his hands up too. But real quick questions for you. One, what software are you guys using to process your raw imagery? And then two is, what are you using for scale when you're putting these large models together? I know some of them, like the landslide going over the highway, you could use the width of the highway to determine scale. But you know, when you're mapping out the modeling the waves, just curious about the scale and how you distinguish that.
Jerry, do you mind if I take it?
Go for it.
So the USGS does not promote any software packages. I have to disclose that first. But we use Agisoft Metashape. It's a neat program. It has more knobs and things to play with, which could be good. It could be bad, because it can, if you tune too many knobs, my musician son will tell me, you can get some really sounds that you don't want, right? And so there are other applications, other software packages that have fewer knobs and can be easier to use. I hope that helps. One of the, with respect to scale, one of the really neat things about having survey grade positions of your cameras included. So if you have that GPS system in there, our accuracy of where that photo was taken is within sort of a decimeter. Often it's within centimeters. The cool thing is that once you start linking all those measurements up together and building a photogrammetry model, your scale is near perfect. It's like in the 10th, 100th of a percent. Relative scales. Your position, we've been doing a lot of work with hurricanes on the East Coast, and when you fly multiple lines back and forth over like the Outer Banks, your horizontal and vertical scales are accurate within 5 centimeters, just using the airplane GPS. It requires survey grade solutions and also really accurate timing. And Jerry sort of emphasized that a little bit, that timing is really critical. But if you can do that, wow. And the surf zone stuff, we actually put ground control. We had that surf zone, the waves, we had ground control. We did not try to do that without ground control.
We do have a quick question from YouTube, which I think fits well with that, which is, there's a question if you've ever used drones instead of airplanes.
Do you want me to handle, Jerry, or?
Yeah, go ahead.
So drones were our first sort of thought on solutions, and they're fantastic. That said, we can only operate drones line of sight. So you can only fly them as far as you can see. And we wanted to capture miles, hundreds of miles of coast, big scale things. And so obviously we couldn't do it with drones. A couple of our maps of the Mud Creek landslide were done by drone because our airplane couldn't get up there. There's certainly advantages in terms of scale with drones. Unfortunately, right now, the Department of the Interior, which we work under, we are not allowed to use drones. We're hoping that is lifted soon. But so right now, we're sort of, unless you have a really big event like what happened on the Big Island of Hawaii with those lava flows, we can't use them. So.
Jump in, John. It's all yours.
Oh, thank you. So that's mind blowing, and I'm thinking of like Nick, and I thought Jonathan's hand was up as well. Probably a million questions. So, but I just in a nutshell, serendipity and teamwork seem to be like interacting with available technologies that you're putting together in creative ways, and the synergies are just mind blowing. And so you guys are literally changing the way people do this stuff, which is really exciting and very cool. But I'm wondering about, from the student's perspective, like watching what you're doing, you have experts in sort of electronics and plumbing and optics and photography, but also like welding and fabricating and CNC. Like what's the full range of tools that are needed to bring one of these things to fruition? Is it just the two of you, or you've got a big team, obviously? So what kind of other trades get into the mix?
So I can take that one a little bit. So at least from the, I work in the marine facilities group. I'm an engineer. Where the USGS is split in kind of in the West Coast office out here. We're split into kind of two centers. It's actually separated. We're in the same building, but it's separated by Santa Cruz Bicycle Factory. And on the shop that I'm in, we've got all the we've got a full machine shop, welding gear. We've got CNC. We've got we are a small group, so we all have to kind of overlap a little bit. But we definitely have we have a set of electronics technicians, a set of software guys. We've got welders and all that, so forth, and so on and so forth. On the science side, we've got our the people that really get into the data side of things and building the powerful computers and the nitty gritty of what is the best kind of memory and what not to use. But we all overlap. We're too small of a group to be one trick ponies. So we all overlap, interact, but there's always one or two of our people that know kind of a little bit more about certain areas. So you always, again, the serendipity kind of thing, we work together. But it's we're pretty fortunate out here in that we've got the full range of stuff we can do.
Let me add to that, and and for our coral reef work, we're working across the country, and we're working with a project leader out there, 𝐂𝐚 Yates, who's a world-renowned expert on coral reefs and their chemistry and things like that. And she knows all the people. We don't do coral reefs. I know this much about them, and Jerry knows this much about them, but we have technology that might be used for it. And working with Kim is fantastic because she's this scientist who knows the people, she knows the questions, she knows the places, and it allows us to sort of fit right in. So having that distribution of expertise and interest is really critical.
Great, I think Jonathan Warnock had a question.
Yeah, thank you. One part comment, just following on the extremely small world line of thinking. I also collaborate with Nephra Matthews on photogrammetry. So yeah, just a ton of coincidences. Along those lines, one of the things we struggle with the most is light conditions when we're trying to make our models. So do you have to be really careful when you fly, or even underwater when you drop the RV in there? Is sunlight really important on that scale?
So I can talk about the underwater stuff a little bit. Yeah, the water clarity, yeah, we don't have to have perfect water for this to work, but we definitely need to be able to see the bottom. It kind of works in surprisingly cloudy water. And you get problems with in the midday when the sun's coming down from directly above, where there's a little bit of wave focusing of the light and creates this kind of, rippling patterns of light on the bottom. But some of that's accounted for by having the simultaneous cameras working together. It uses that. It can actually use that on low feature areas to find the angle differences between the cameras. And then of course the air photo stuff, I mean, I can let John talk about that.
Well, first I'm going to say hi to Nefra for us. She's a great colleague, and I haven't seen her for a while. It's been a year and a half. So if you get to see her, please say hi. Secondly, yeah, we've been, blown away is one way to think about this throughout. One of the neat things underwater too, and this is yet to be tested, but my hypothesis is some folks have had a hard time with really bright light conditions in corals and shallow water SFM photogrammetry because of the way the surface bends the light and makes bright spots and dim spots, and that changes, and that becomes the dominant sort of feature, these light beams underwater. And the neat thing about the multi-camera setup, the 5-camera, is that it captures those light patterns in multiple cameras at one time. And my hypothesis is that we're actually doing a better job in bright conditions with that multi-camera system. That's just one thought. The other thought is I'm really impressed with the way the aerial system works. We generally try to have it flown in well-lighted conditions on the West Coast. That's afternoon, so we're illuminating the beach and the cliff. It seems to work a little bit better when it's diffuse lighted rather than heavy shadows. Sometimes in heavy shadows we have areas that have no data because they're in the shadows and they're so dark there's no data in them. But in general, it seems to work well, and we also do a processing technique where we link flights together. We process different flight dates together, and that improves our accuracies. And those seem to work even in different lighting conditions. So, yeah, it's kind of interesting. I was worried a lot about lighting early on, and lighting has generally not a factor. It's if we can see it in general, we can kind of map it. Is what we're thinking these days.
Ken, you have a question?
Yeah, I was curious to know if you've had any reaction, or maybe there's an overlap of techniques with the folks at the astrogeology office in Flagstaff, because I look at this and I think about not just about a play, they're trying to get the shape of planetary bodies without ever being able to walk around on them or survey them. And there's no GPS in Mars, where of course we know there's sand dunes moving around and landslides. But I would think this would be even more exciting in a place like Titan, where we see these features that look like they could have been active, but it took them years just to figure out they were seeing lake surfaces and not empty lake beds, because they didn't know what the properties of ethane were. Just curious about that application.
Jerry, you want to note the camera and on Mars?
Yeah, so one of the so I was reading about the drone helicopter on Mars that they just flew, Perseverance. Is that what it is? Or it's well, anyhow, the cameras that they're using on there happen to be the exact same brand that we're using in the squid vehicle on those coaster cameras. So I thought, all right, cool, we picked the right camera. But as far as scaling things, if you know the distance between the cameras, then you can get really precise relative distance or measurements of things in your view. So you could use it to measure the size of things, not the position of where they are necessarily, without a position of where the camera is. I don't know, without a GPS constellation, it's hard to tell where you are on other planets. I'm not sure how that works, but you could definitely use it to measure the size of things. They might be, I don't know.
In terms of USGS collaborations, we've worked primarily with the landslides program. So we are in the coastal and marine program. And so what you've seen today is a lot of coastal and marine stuff, and that's because that's our mission of our program. We've worked a lot with the landslide hazards program in mapping landslides, especially along Big Sur. We've also are starting to work with our earthquake colleagues and thinking about rapid response to earthquakes, especially out here on the West Coast. If and when we have one, how do we go out and collect data as soon as we can to map what happened? We do a lot of work in hurricane response too, especially on east and Gulf coasts. We haven't talked with our astrobiology group, and that would be a neat conversation. And just one thought, and what wasn't emphasized earlier, is that one of the neat things about these type of data is that, and this type of processing, is you can use almost anything in the electromagnetic spectrum, any imaging data. And so you could use stuff in the infrared or thermal infrared or, any portion that you can collect and do similar. So I've seen people use thermal infrared. It's the lower quality data, but you can actually use it in the processing scheme and map temperatures. And so the thought there, and the interesting part about this is that, and I think Jerry was emphasizing this with the coral reefs, is that you get these, not only you get these 3D products, you get this imagery, this other data. And with our cameras, it's red, green, and blue, right? It's the color of what you're looking at. But you could also introduce other wavelengths, more specific wavelengths, narrower wavelengths, et cetera, and start mapping features and determining features, especially in remote locations, whether they're on Earth or elsewhere.
Great. We have another question from YouTube. This one is going back to the slide that you had up of the Coastal Records Project, showing the change, showing the point cloud and the change. So if you could pull that slide up. And the question is that it looks like between 2008 and 2009 that there didn't seem to be any erosion or accretion detected. And is there a known reason for this? You're on mute, Jonathan.
Thank you. That's a great question. Absolutely. That's the science of it. So here, so that's in just south of San Francisco along the Central Coast, and we and so go back way further, Jerry, to the.
It's the Coastal Records, the Helicopter Coastal Records Project.
Oh, okay. Sorry.
Yeah, the time series, and here we see a so along our coast we have a number of things. That one, right there you go.
Nope.
The one with the erosion.
One more.
Next one.
That one.
By the way, Gabrielle and Ken Adelman are the ones who got sued by Barbara Streisand, and there's an interesting thing called the Streisand effect, which you should look up on if you're need to do something fun this weekend, which comes from them. So small world. Anyway, so I don't know why I brought that up, but yes. So see there in 2008 and 2009, there was very little change along that cliff face, and so one of the primary drivers of coastal erosion in California are the waves, or sort of wave attack at the base. There's also, of course, hydrologic effects of how that material deforms and collapses, and that's often related to water content in that material. But so you have those two sort of things working on. And of course, you have the geologic structure, right, which is really important too. So you have those various things. And here, what you're seeing in from 2004 to 2008. And then 2009 to 2010 is erosion primarily in the talus, in the really loose material of the landslide, and that's done primarily just by wave action. So when waves come up to the base of that material, it's very easily mobilized and moved, and then the rest of that loose material kind of will slip down. And so we saw that in those two intervals, but we didn't see a lot of that in 2008 and 2009. And that's primarily a function of the beach was wide enough during that year and the waves were not large enough so that the waves really didn't come in and attack the base of that loose material. That's the general idea of sort of how these processes work in California. And hopefully that made sense.
Great. Thank you both. I want to thank you both so much for this wonderful keynote address and for being game enough to try the tag team presentation. It was great. And personally, I want to thank you all for your help as well over all the years on projects that we've worked on together. So anyway, thank you. Large applause if we were in the auditorium for you there.
Katie, we appreciate all your collaboration and help and the fun we've had over the years. If there's anything of interest from this talk, have people contact us directly. You can find us in email, etc. And this was an honor to do.
Yeah, likewise. It was great. Thanks.
Thank you. And Jerry, next time you're back home here, I might make you come and
that'd be great. I'm totally into that.
Take a look at some more stuff with us. So.
Sounds good.
Great. Well, so this ends our 47th annual Geoscience Day. And I want to thank all of the presenters and all of the faculty and students and the families that have all, and friends who've all tuned in today, whether you were here on the Zoom meeting or following along on the live stream on YouTube. So congratulations to everybody.